All right. Thanks again, Ollie.
No worries.
All right. There's the YouTube stream. Okay. We are live, everyone. Thank you, everyone who's here for showing up for our fourth and final session of the third annual Reddit Robotics Conference. We have seen amazing presentations and keynotes so far, and we are only going to continue seeing more amazing ones in this final session. So without further ado, let me introduce our keynote speaker for this session, Joe Castagneri. He is the head of artificial intelligence for Robotics, and Robotics is trying to integrate recycling and robotics in a way that will be a greener way to recycle and give higher yield to our recycling processes. So with that in mind, Joe, please take it away.
Great. Thank you so much for that introduction, and hello to everybody. Thanks for joining. I'll just get the presentation up and away we go. So I'm going to spend some time talking about Robotics, the company here I'm representing. But before that, I kind of want to talk with this group about robotics in general and some of the dramatic and quick increases in the applications of robotics in current markets that we're seeing today, and some of the technological factors that have led to that. So if you could join me for a second, think through really what is a robot? Get something into your head, take a moment and picture a robot. And of course, this is a community of experts, so you're probably not thinking of this. Maybe you are. A lot of people, when they picture a robot, might think of the Jetsons, a human-like helper around the house that is doing things that humans would normally do. So an anthropocentric view of a robot. People in this room might think something like this. One of the most successful robots commercially of all time, the Roomba, which really is as far away from a human as you could possibly get, right? Like it doesn't have eyes in a conventional sense. It's sensing in a different way. So very different than our Jetsons view. If you're a little cynical, you might think of something like this, especially as you're seeing AI news as it accelerates. But truthfully, while the pop culture is fun, and as many of you know, it's not really accurate for what it really means to be a robotic system. So what I'd like to talk a bit about today, before telling you about Robotics and how we're applying robotics and artificial intelligence to the recycling industry, is just this idea that robots are everywhere. They're driving efficiency in our everyday lives. They don't look like humans. They don't really have to look like humans. But since 2014 and advances in computing and modeling, we have this massive increase in what robots are able to do, which is allowing robotics to be applied into industries that up until now were completely off limits for things like robots. So continuing on, when at AMP, when we think of robots, we think of things like this. So if you kind of take the top right there, that might be the most conventional commercial application of robots in assembly line. Automotive manufacturing, where we have the repetitive movement, taking a car door and mounting it to the chassis of the car. It's always going to be the same every time. Obviously, that's a very constrained problem. But you also have something like the bottom right, an airplane, right? An airplane, I would call a robotic system. Sorry if this is news, but the pilots actually do a decreasing amount of the piloting work for a plane. They're more for redundancy than the piloting of the plane through the journey. Now, a robotic control algorithm for a plane, a lot more loose environment, unconstrained than what we see on the assembly line, but still you're in 3D space up in the sky. Collision risk is not what as at issue. It's more route planning. So still some freedom in how we design that robotic system. But I would also point out the power grid. The power grid is a robotic system where we are constantly balancing demand and supply of electrical power through different subgrids, and we have to know when to connect them at the right time and have that connection executed within, you know, a 60th of a second if you're in North American power systems. And so that is a super wide distributed power system that I would call a robot that we all rely on all the time, every day, to the degree that we've forgotten about it. Stock market, I would call a robot as well. A lot of algorithmic robo trading is, you know, measuring different market forces, computing what a good trading strategy might be, and then executing that strategy. And then I put, you know, the biggest picture in the middle is, of course, you know, I'm here with Amp Robotics. We put some Amp robots. We, of course, think of our own robots when we think about robots. But all of this kind of has led us to a definition I'd love this community's feedback on to define a robotic system. So what's common about all these things? Well, we would say being a robot boils down to three things. You can sense things in your real world. You're going to do some sort of brain power over what you sensed to make decisions. And you're going to take the results of that brain power. You're going to use those observations to do some real action in the real world. So in some of those examples from before, in the example of a plane, we are going to measure our location with GPS. We understand what our yaw and our pitch and our roll is, what the velocity of the plane is, what the acceleration and thrust coming from each engine is. And through those raw sensory observations, we can compute, hey, you know, I should put incrementally more thrust power to my left engine because I'm off course. This will correct course. And then we execute that thrust change, remeasure, and look at that. We've taken a real impact in the real world. For the automotive manufacturing, it's a lot simpler. We're not sensing much. We're sensing feedback from torques as we're torquing bolts, compressive feedback as we're like mounting the door to the chassis of the camera of the car chassis. The processing is also super simple. It's all pre-computed, right? Like I'm going to take this path, I'm going to grab the door that's always going to be here, I'm going to place it there. So that's a far simpler robot. What I want to talk about is how the history of robotics up to this point has been significantly simpler systems with constraint on how complicated this decision-making part two can even be, because we just didn't have algorithms and we didn't have hardware to do really complicated sensing in part one. And both of those meant that there was a limit to the real world actions that we could support, right? We can do really cool things with robotics and automate things in industry, but you couldn't teach a robot how to tell the difference between different types of recycling and have it sort it by itself. One of the keynotes today was Scythe Robotics, which, by the way, also a Denver area robotics company. Amp Robotics was also founded in Colorado, so shout out to Scythe. They're using similar technology to be able to automate away a task like mowing grass, which to humans might seem simple, but is actually so much more complicated than our example of the car assembly line process. So let's get a little bit more specific. I'm curious to read in the chat later what people think about this definition. I'm very up to improving it with your feedback. But let's get specific. How are robots changing industry? And then I'll get even more specific. How is AMP doing that in the industry of recycling? So we talked about this already. I'll go quickly, but just to double click on the idea that these existing systems have fewer constraints on what it means for them to work successfully. It's really hard to autonomously pilot a plane, but you also, in some ways, have a lot of flexibility. The plane doesn't have pedestrians to deal with, unlike self-driving does. In the automotive manufacturing application, everything is so designed for the robots that the robots are allowed to be dumb. The robots don't have to be particularly smart to add value. And so let's see how the intelligence of robots can increase as you increase the tech that's driving them. And this means that I get to give you my first graph, big graph guy. I want to talk about GPUs and how they've been improving so rapidly in the last decade and a half. A lot of the folks in this room are likely familiar with NVIDIA GPUs and the toolchain on top of them that allow for strong computing. But if you're not, a GPU or graphics processing unit is a chip in your computer, just like the CPU that runs the normal part of your computer. And it's really good at doing matrix multiplication, which seems like such a simple thing that might not matter, but In a broad sense, GPUs do a lot of math really quickly. And we've been able to make GPUs better and better each year, such that we can do way more math than we could, 5 years ago. So case in point, if you look at this graph down here, all the blue and the light blue lines, those are the improvements over time in CPUs, where this y-axis is gigaflops, so billions of floating point operations per second that one of these chips can do. So how much math can you do per second? And you can see CPUs they're definitely getting better from 2000, and this ends in 2014. And I'll comment on why I chose that year as a cutoff. But the green lines are what draws the eye. Green lines are the same metric, but for GPUs. And look at this just massive exponential explosion starting in the lead up period before 2014. What is remarkable about this is that it's kind of a specialization of compute technology like GPUs. CPUs are really good at a lot of what CPUs do. GPUs can do this distributed math of a lot of high precision required floating point math with these big algorithms very quickly in a way that's specialized, in a way that's also getting way better over time. And what we see here is a sort of, if you build it, they will come idea. If you have a really great compute platform, it's only a matter of time until algorithms start being used on those compute platforms that can take bigger and better advantage of the hardware. So you have a simple chip, you got to write a simple algorithm. You have a really powerful chip, you can run a really powerful algorithm. And if we take our earlier definition where we want to be able to, sense really complicated things, well, you can't really sense complicated things if you can't compute on complicated things. So the bottleneck to robotics up until about 2014 has been on the algorithmic compute side in some ways. Let's look at another very similar graph. Note the years. There's just like a 2-year offset here with the complexity of algorithms over time. And so, of course, you're getting me in this presentation. I lead AI at Robotics, so I care a lot about the models and about the GPUs. And so we've put an example here in the top of an image of a 2-stage object detector. This is, I think, MASCAR CNN. So the point of an architecture like this algorithm, you feed it in an image, and it will learn how to localize all of the objects within that image and then classify each of those objects within the image so that you can do stuff with it. This is a pretty complicated diagram, right? Like there's just a lot going on in here. Each of those rectangles is usually thousands of numbers, and we're doing thousands and thousands of matrix multiplications to look at even one single image. That requires a lot of compute. Back in the day, so let's talk about this graph number 2. So similar, we're looking at publication date on the x-axis, on the y-axis, instead of looking at like gigaflops like we were before. We're just looking at the number of parameters in the model. So this is a proxy for how complicated of an algorithm can we use for different tasks. And then the shapes here are different domains. So you have gaming, you have large language, like GPT would be the most recent example of this, other, which is everything else. And then vision, which is where Robotics puts its time. We're doing computer vision for robotics. And if you go way back in time to the 1950s, very simple computing is just getting its start. We can't do that much more complicated of a model than something like y equals mx plus b, right? That has 2 parameters, and we're taking one sensory observation, we're predicting one output from it. And this logarithmic graph shows you that around 2014, there's an explosion, right? There's an explosion of parameter count in models, which, going back to this, seems maybe like those two are related. 2014 is right at the end of this graph when you suddenly have massively more compute power in these chips. And if you look at the magnitude on the y-axis, in the modern day, it's very common to have hundreds of millions of parameters in your model, which is obviously incredibly complicated. And so going back to just applications in industry, if we think about, we want to automate something, we want to apply robotics to this field, well, we have these constraints like it might be in a dirty environment. I'm gonna have a power budget where I can't run I can't run infinite compute. I have a latency budget because it might need to be real time. All of these things that make it really difficult to run complicated algorithms. But as the compute has gotten dramatically better, that barrier to entry, which has been, hey, we just can't run that complicated of an algorithm on the hardware in the field, it goes away. That constraint relaxes, and suddenly you have this explosion where we can apply robotics in arenas where it's been impossible to up until now. So let's give a case study of this with AMP Robotics. I'll get a little bit deeper as we go on, but I think recycling is a good case study for this. Let's just talk a little bit about the recycling industry for a second. The task of a recycling facility is to take all of your recycling that you put in your bin. It goes on your curbside. It's taken by a carting truck that brings it to some big facility that's generally a maze of conveyor belts. And the value that that facility provides is, hey, we've got all this good material, but it's not valuable if it's intermixed. I don't care if I have this one type of plastic if it's also intermixed just as much with paper, because a downstream process can't take it unless it's separated. So the problem here is the problem of sortation. We have to sort the value apart, and in so doing, we recreate valuable commodities that people are willing to buy. But it's a really hard classification problem. As an example of this, just think about all of the things that maybe you have put in your recycling bin, thinking, yeah, they'll find a way. They'll find a way to recycle this lamp. You can't imagine the variability that ends up in a recycling facility. We see everything from bowling balls to full bicycles to carpeting to unfortunately used diapers. So it is highly variable, unlike the automotive industry of manufacturing where you can control your environment. It's dirty because it is literally trash. And because of some of the things that are placed in the trash, it is dangerous. And so all three of these, the 3Ds, they make this a perfect automation problem, which is why it's so exciting that something like this could be automated. Until recently, it was way too difficult of a task to automate. There are hundreds of different categories that you have to know. Everything is moving in a real-time application down a conveyor belt. And so traditionally, people have been standing on the side of the conveyor belt and sorting out, the milk jugs from the drinking water bottles from the cardboard, et cetera. So let's get a look at AMP's system. AMP makes Delta-style robots amongst other variants, but the way that we got our start was with this kind of robot. So we have a Delta-style robot hung in a safety cage that goes over the conveyor belt. So you can see in that image, conveyor belt is passing under an RGB vision system. And we're processing that sensory data using an algorithm that is deep learning, right? So deep learning computer vision and performing object detection, tracking those detections over time to fuse them together, optimizing what we harvest with the harvesting algorithm, and then through path planning, commanding the robot to go intercept this material at this location at this time. And we sort using suction. We just use pneumatics, right? So just go down to this location, turn on your suction system with the suction cup gripper at the bottom, and then place that material off to the side of the robot. The value proposition of this is, like I said, those humans that are performing this task historically. The issues that existing facilities see is because this job is so dull, so dirty, and so dangerous, retention is really hard. I've heard a lot, it depends on where you are, but average tenure of a recycling sorter can be as little as 4 weeks. So you're turning over your staff really quickly. And you can imagine this is expensive for a recycler. It's expensive to have a marketing budget to find new people, to train those people as they come in. It's expensive if they no-show and then you don't have somebody pulling material that day. And so having a reliable autonomous solution that can retrofit place where that human used to be, that doesn't take sick days, also can see everything better than the humans and more accurately, and can move significantly faster than the humans, is just makes the existing recycling industry far more effective. And I'll get more into that later. But you can see here the kind of the thing that matters to customers is, well, a human is doing 40 or so picks per minute, and that is their proxy for revenue, right? I'm pulling off this material and I will ultimately sell it at some price. So if we can have a robotic system double that or triple that and do 80 plus picks per minute of valuable material, then this expensive system that is complicated and technologically complex can not only pay for itself, but make the total business operation of the facility run better. So let's go a little bit deeper into that. Why have these changes in technology and in the greater industry allowed us to do this? What's different now, and how did we get our start? So our issue with the world right now that we're trying to tackle is that we go to all of this trouble as a species to dig stuff out of the earth, energetic sources that we then refine into fuels, or precious metals that we refine into finished product metals we can use for manufacturing. We go to all of this trouble, and then we use it once, and then we bury all of that valuable stuff right back in the ground only a couple of months after we finally finish making it. This stuff is valuable. You have energy-rich fuel in the form of plastic bottles that are being buried in the ground. You have paper products for burying in the ground, and you have precious metals like aluminum and ferrous material, beverage cans, of course, made out of a pre-refined alloy of aluminum that we're burying in the ground. This is billions of dollars a year that we're burying in the ground. Wouldn't it be cool if we didn't do that? If we could mine that value out of the waste stream instead of going back to the planet and mining it out of the actual existing natural resources. So given that, like, our mission is to enable a world without waste, we're trying to apply advanced technology in the form of robotics and artificial intelligence so that we can take the existing recycling business and industry and make it more efficient by giving them solutions that increase their profit margin, right? So that they can be a more successful business. But we also want to fundamentally change how we recycle so that we can make this economy as circular as we can, where there is a place to put the thing that we went to all the trouble to mine in the first place. So we were founded in Colorado in 2014 by Dr. Matanya Horowitz. He grew up in Colorado and had an illustrious academic career, ending up in Caltech doing robotic path planning for his PhD. And then right after finishing his PhD at Caltech, I guess he got bored in a couple of days, because then he founded a company in Golden, Denver area, Robotics. And we were initially grant funded to try to find solutions to the classification problem of, hey, you got waste and a cheap optical system to look at it, and then B, the robotic problem. Can we now sort that out? So over the last, I guess 7 years, we've grown to nearly 300 employees. We have a full engineering team between hardware, software, embedded, and facilities. We have an operations team that is building, installing, servicing, and maintaining our fleet of nearly 300 robots that are installed across the domestic United States, some in Canada, some in Europe, some in Japan. And then we even run several facilities of our own so that we can start tackling a bigger scale and a bigger scope of making recycling more effective. So these kind of key statistics, we do have several hundred robots deployed globally. We'd like to add, another order of magnitude to that, and get into the thousands. But we've learned a lot of lessons by managing a fleet of distributed robots that are all in all of these various conditions in all these various facilities. And those facilities, the 275 robots, are spread between about 80 different facilities. My favorite acronym in recycling is MRF, Municipal Recycling Facility. These are where the recycling is done, that maze of conveyor belts. And then a statistic I like that just keeps going up is we, through all our systems, see more than 50 billion objects every year. And every system that we install, it adds more to that statistic, which is just really cool to consider. We have all of these eyes that we've installed across the world that are constantly localizing, predicting, and then egressing analytics on all of these objects that we've seen. So how does it work? Let's return to that definition of a robot, right? We have what are we using to sense? Just RGB. We're just using an RGB camera, and it is not even that crazy of an RGB camera to image material. We have a camera frame to control lighting really well, and we're imaging a conveyor belt as material passes underneath it. The second part of our definition of a robot, where we're doing something with that sensory information, processing it to come to a decision. The brain here is an edge compute system where we're running fairly power heavy GPU to run a deep neural network that's big, so that we can do object detection and classification of the things that we saw. And then what's the real action that we take? We have hands. We have the robot go to where the object's going to be at the right time and remove it from the belt. But we can add a fourth thing. We can add a fourth thing here, memory. You don't need memory to be a robot by our definition from before, but it sure is helpful if you do. We have this fleet of robots that has been looking at the waste stream every day for every second for their entire install period. So we can egress that data and understand what is getting recycled. How could we make this more effective? Is this unit being used to its optimal capacity? And so we egress kind of its surmisings of what it's seen up into the AMP cloud where we can process it. So it's enough of me talking. I'll show you the video so that we can kind of talk over that, see the robots in action. This is going to be a little laggy, so I'm also throwing just a YouTube link to a similar video that we have in the chat. Feel free to check that out. And I'll loop over this, but you can see that robot is just placing stuff from the belt off to multiple drop locations, so it can independently remove things from the belt and sort into multiple fractions, right? So you can take your water bottles, put them here, and your milk jugs and put them there. And on the right, you can just see visualizations of our AI actually functioning. So that's just an overlay of our, here it'll come up here in a second. It's an overlay of our vision system actively classifying, localizing those objects. And you can see they move pretty quickly. They have to add value in this application. They have to be as fast as humans are, and ideally they have to be way faster. And so they also kind of have to get everything that they can. It's a recovery-oriented economic problem. So 2 notes to leave on, and then I want to make sure to leave a lot of time for discussion, because I want everybody's feedback on how to define a robot and where we see applications going. At AMP, this wouldn't be a possible problem to solve without the massive amount of research that has gone into deep learning, starting with AlexNet in 2014. It wouldn't be possible with the massive amount of compute improvements that were made by NVIDIA. And this allows us to do a pretty transformational thing. We can look at something like recycling that everybody can agree is a good thing to do, but is famously hard and not very profitable, and not everything is recycled. And so can we make that industry an attractive place for people to innovate in, rather than a place people run away from? To date, recycling's been it's been technologically behind. It's been underserved by new technological solutions because it's so hard. But once the brains kind of crosses a certain threshold, boom, you can apply this new technology in a way that can fundamentally innovate the entire problem. So here we've been talking about, oh, what if you had a robotic system that just adds a lot of point efficiency? You can save that facility cost by not having a human do the automated task. But then you can very quickly start asking a far more interesting and more compelling question. How would you design the facility itself if you could design around the fundamental building block that is this really efficient robot that is way faster, way more accurate, and doesn't take the downtime of a human? This is where AMP is going. And when I mentioned that we have 2 to 3 facilities that we have built and operate, those facilities are designed by us, and we just buy trash and we sort out recyclables, and we can sell those recyclables back into the market. And because they're starting from a technical foundation that is fundamentally more efficient, those entire facilities can be fundamentally more efficient. And things that today are not recyclable because it was too costly to recycle them, the opportunity cost of removing this thing from the line was too high. Well, now they are. They suddenly are recyclable because we've reduced the cost of sorting them through the use of this technology. So the reason I dwell so much on the technological improvements in the industry of computing and in the academic field of deep learning in particular with this group is not because this is news to any of you. You're very familiar with the goings on here, but it's a challenge to ask, hey, if this is working in recycling, what new industries that before the problem was just too hard to tackle with automation and robotics, what industries are now accessible to this problem? We did hear from, I'll plug Scythe again, like the autonomous grass mowing problem was not something that we could solve with technology until the last 5 to 10 years. And sure enough, we can add value to those landscaping companies today. Same thing for AMP. This was just too hard of a problem to possibly try to automate until 5 to 10 years ago. So that's not special about recycling. There are plenty of things that were just out of reach for robotics and automation until today. So that is what I've got kind of prepared. I would love to dive into any questions that folks have with the remainder of the time.
Yeah, let's go ahead and do that. So, I mean, first off, thank you for presenting. What a great presentation. It's so cool to see the like real-time classification happening so quickly, between all the different types of classification. You're totally right. I think everyone's had that experience of, looking at the number inside of the recycling symbol and being like, what does this mean anymore? Can I recycle this? Do I have to look up what my city does? So it's nice to have these systems in place to be able to sort. One question that I had, you said you guys build these Delta arms in-house. I know there are a lot of, large robotics companies that make, general use Delta arms. Did you try any of those? What led you to design and build your own? What challenges did your own design solve that others couldn't?
So that's actually a key thing. I might have misspoke. The Delta arm we integrate from Omron. So we do use an off-the-shelf Delta arm. And I'd remark on the strategic purpose of that. When you're trying to apply robotics in any real setting, no matter what you do, it's going to be really hard. So choose the hard thing you have to solve. Don't add extra hard things if you don't have to solve them. So our path planning and pick and place needs and speeds were satisfied with existing Delta arm variants. We tried several through ABB and Omron. We considered building our own. We did have custom platforms that weren't Delta style ourselves too. But when you build your own robot, the reliability and the sophistication of engineering to hit the reliability spec that you want to put something in industry is so hard that many huge companies exist just to solve that problem. And so for us, we very consciously elected, let's not add a separate really hard problem to our plate. We're going to focus on the problem of integrating and applying this technology into the industry, and that's going to be plenty hard for us.
Absolutely. Yeah. I my field is focused more on the robotic arm side of things. And every time I hear someone talk about wanting to, design and build their own arm for some specific purpose, it's like, no, you're never going to be able to, the amount of time and money you're going to spend on research to get anything close to something you're able to buy off the shelf right now. It's just crazy, which is why I asked. But someone did ask, what's the life cycle of these arms? Can they, it's a very harsh environment, can they work for months, years, decades?
So years, at least so far, as we've definitely had many in place for more than 5 years. Big shout out to Omron here. They make a really great robot that can go through many millions of cycles. One technical consideration that really means that we're abusing these robots One of the hard problems that we're not solving is depth. It's just an RGB camera. We're not even doing stereoscopic depth for these. We could, and it would make it better, and we want to, but we historically haven't, which means we are slamming into material. So if you have, we've done a lot of mechanical engineering work on that end effector to make it robust to this slamming. But you can imagine, there's going to be a lot of moments moving through that whole robot as a result of that. And these robots still, like Omron's manufacturing and engineering behind them means that the upper arms, at most, the most complex thing that we'll really have to do for an old robot that's maybe been tuned poorly, so it's getting too much force into that belt, will be a fine upper arm calibration, which is not actually that hard to do. They don't have, you don't have to change the oil on them. They do actually self-contained, just work. They're also designed to, excuse me, they're designed to break in good ways. So like normal Delta variants that y'all have likely seen, the lower arms are carbon fiber and will break. And the cup bearings in the carbon fiber are only rated to, many millions of cycles. So there is a routine maintenance to these robots, but the core robotic platform definitely has been in place for 5+ years and doesn't show any signs of slowing down.
Interesting. Yeah. So you guys are doing a 2D localization, and then are you just assuming that stuff is going to be on the height of the conveyor belt?
Yes. So 2D localization, it's even trivially, since it's a conveyor belt, ideally it's a one-dimensional motion problem, right? You hope that things aren't rolling on the belt. If they are, as long as the velocity of rolling objects doesn't change after it leaves your camera view, then we can and do get them. But if you have any acceleration across, not with the frame of reference of the belt, obviously it's going to be hard to find that thing. But yeah, so again, like choosing what are we going to make hard here and what are we going to make easy. We could have done and really considered, let's do stereoscopic depth assisted by IR would be one great method here, and have our path planning include precise Z-coordinate tuning. Or we can make a really robust high travel end effector that can take the variation between where things are. One applicational thing that's important here, it's already trash. It doesn't matter if I smash it. In fact, smashing it actually might make a better grip, right? Like we might actually improve the grip that we get. And so when you're looking at your application, sometimes it's important to see, hey, what are training wheels I can literally put on, because it doesn't matter if I don't do the rigorous thing. And in this case, yeah, the 2D tracking with really 1D motion, and then descend to belt height routinely with give in the end effector was our solution.
That is a really interesting consideration. Just saying, like, because I would probably say 99% of robotic, implementations, you do have to be very careful about not smashing into stuff as you're operating. But you're right. Yeah, it's garbage. So what are you really going to do? Turn it into more garbage? Yeah.
Totally.
Someone had some questions about the kind of financial model, I guess, of your company.
Sure.
Is it really profitable right now to sort this waste and sell the sorted waste? And I guess more broadly, as people who are interested in, I guess, recycling and reuse as a more green application, it is a little frustrating to see this being held back a little bit by the considerations of profitability. Are there grants in place that just say, you don't need to be profitable, we just want you to be able to sort and reuse this recycling?
Absolutely. And overall, from a macroeconomic perspective, we need to encourage the things that we want to happen in the private market. They won't if they're not profitable. We dearly want these things to change and technology to improve, but the best meaning group of folks still needs capital to do it. So through green incentives, it makes it a lot more accessible so that you can promote technology development. A couple of things in AMP's history. Number one, We actually got our start through DOE funding related to this problem. So there's actually a pretty tremendous amount of waste diversion, classification, and sortation funding through DOE-related programs, laboratories, national laboratories like NREL in Golden and the Idaho National Labs, National Laboratory are all doing things in waste conversion processing. So that's great. There's a lot of public funding for these types of things. The second layer is there's actually a big maze of granting for the facilities. So municipal recycling facilities typically have a contract with their municipality where they are going to take this tonnage of material and process it per year. And that can give them a premium incentive relative. If they were an independent person, not independent company, not partnered with the municipality, it'd be more expensive to source the material. And so they're kind of priced into helping the municipality because the municipality has said, yeah, no, it's worth it for us to have better waste diversion, and we're willing to subsidize it by ensuring, access to material at certain prices. The third area, and where it came in for us initially, like we're trying to sell these complicated systems. They're expensive, they're big. This is not a screamingly profitable industry. It is the one misconception is people think recycling isn't profitable. It is, but it should be more. But it's weekly profitable in a way that means that you don't have like a whole bunch of cash to just buy a whole bunch of robots. And so we partner with a lot of granting groups that are, for example, really interested in seeing under recycled objects get recycled more. And they'll do something. There's one group that was early in AMP's history called the Carton Council. So they're not a group of hooded and cloaked men in the corner that talk about cartons. They're just a granting group that wants to see cartons, poly-coated fibers get recycled. And so they will help a given facility procure an expensive piece of heavy equipment as long as they use that to sort cartons. So there are a whole bunch of different incentive structures with a combination of public funding money, but also private entity, nonprofit grant funding money to provide easier access to higher technology sorting equipment and build markets for material. This is where we're really interested in helping. I mentioned before, you can see one on the screen right now. Red Solo cups are made out of polystyrene, number 7. And polystyrene is not a very recycled plastic. There's not a huge market for it. You can sort it. It does have value, but generally the opportunity cost of picking that polystyrene cup instead of a PET bottle is just too high. So it's not sorted. And if you go to the last conveyor belt in the facility, it's called the last chance line, because anything that you don't pull off of that last belt is going to end up in landfill. You see a lot of red Solo cups. You see a lot of thermoformed clamshell plastics like takeout containers. You don't see any milk jugs, beverage cans, water bottles, or cardboard, because those are kind of the cash crops. One thing we've been engaging with these granting groups I mentioned was, hey, we, with our technology, can sort these things. The reason there isn't a market for them today is because there wasn't good technology to even sort them. We can sort them at a low enough cost that opportunity cost barrier goes away. Let's partner and try to build up an offtake for this material that traditionally isn't recycled and divert material that up until now just goes to landfill. And so I know it is frustrating. Like, why does it have to be profitable for it to work? But that's also how we drive innovation dollars into this. If you can build new markets where there's just a little bit of profitability to it, then it doesn't just become altruistic to divert waste from landfill. It becomes stupid not to. You're throwing money away if you're not. And corporate interests will align behind that incentive. And so with the help of these granting bodies, with the help of public funding, it is becoming increasingly possible.
Great. Yeah, thank you for such a comprehensive answer. That's fantastic. I think one of our other presenters, Daniel, has a question. Daniel, feel free to unmute and ask if you'd like to.
Two even. One regarding your definition of robotics, since you mentioned it a few times. So if by your definition, the stock market and aircraft control systems are robots, And do you think we should perhaps look for new terminology to specifically describe the kind of self-supporting mechanical assistance that the general public thinks of when we use the term robot, or would you want to separate them at all?
Yeah, great question. And of course, as the AI guy, I take a broad view of robotics, which is why I think of the stock market as a robotic application, because real world consequences occur from the autonomous processing of data. I do think that it would help the benefit of being more semantically precise if we split them up is for what exactly? One thing that I think of is if kids in school can see the applications of robotics where they and be interested and where they can help and have a broader view of what it means to build a robot, that's great for the world, for robotics and for the world. So if taking multiple definitions can provide better communication to the community, then I would say definitely. You could say human task replacement robots versus industrial robotics or something like that, just off the cuff. But yeah, I think making a specific definition is great to do, especially if it makes the whole industry more approachable.
Cool, thank you. And another question regarding recycling. What's the kind of acceptable error rate or the kind of acceptable contamination of wrong products in bins that are maintaining these kind of plants? And is it like a barrier that you run against, or is this not an issue at all?
It's a definite constraint. So the optimization problem is we want to maximize the tons recovered constrained by minimum purity. In AI terms, you want to maximize recall with a constraint on precision. It is permissive enough. It's like 1.9. You need 90% purity in the bales for the consumer of the bales to be able to recycle stuff out of it. And it adds expense to that recycling facility the dirtier the material is, because they have to get to 90 and they can only make money off of what is in the bin that's actually valuable. So it hurts the recycling facility if you put something in there that's not recoverable. An example of this might be like my example from before. If you put furniture in your recycling bin, they're just not set up to actually reclaim that. And so their total yield on the material that they get in is necessarily lower because all of the mass that is stuff they just simply can't do anything with, they have to pay to landfill. So it is, as a consumer, like the if in doubt, throw it out terminology and not wish cycling, i.e. putting things in that you hope get recycled, help these facilities a lot. That being said, ultimately the purity constraints are driven by, like I mentioned, the downstream consumption of these materials. Some of them are using a chemical process that require, the chemical resins to be in these proportions with no more than, 2% of that. A lot of them are a lot more permissive. They'll take a 90% pure bale, do one more sort on it to remove the bad stuff, and re-extrude the plastic. Downcycling applications where you're taking a good plastic and then you are recycling it, but into a lower grade material. So taking, for example, if you've seen those park benches that are made out of re-extruded plastic, it's a lower grade plastic at the end of it. As a result of that, it's not a huge constraint on purity. So to concisely answer, purity matters a lot. It matters more if you're doing upcycling or straight cycling than it does for downcycling.
Cool, thank you.
Yeah, thank you. Another quick question from the YouTube stream. How easy or difficult is it to integrate these robots or these sorting stations into existing facilities?
Yeah. That is a big driver of some of our innovation, is trying to make it easier. They're heavy enough. You have a couple of things going on. Number one is, where is the material already in the facility? And is that an accessible place to put a robot? We've gotten really good at taking, gantry cranes and dropping it into really tight fitting places in a very complicated way. But you might need structural members to support the added load that you're adding on the second or third story of a recycling facility. The lighter you can make the system as a result, the easier it is to retrofit. The smaller the footprint, the easier it is to retrofit. And so meeting our customer where they are, problem one was, yeah, the costs associated and the revenue lost from human sorting is really high. We'd like an automated solution. Problem two is very quickly, how quickly can you install these and how much additional work do I have to do in my facility to make it easy to put them there? And so a lot of our newer variants aren't a big, large footprint safety cage robot. We have a robot now that mounts directly over the belt, so it's a lot quicker and cheaper to install. And so I'd say it's one of our dominant considerations in particularly the mechanical design.
Okay. I mean, so your mention of safety cages reminded me of, I'm in the robotic welding sphere, and one of the biggest things that we're looking into with cobots coming out is not necessarily the ability to grab the robot and teach points, but the idea that cobots kind of necessarily require less safety barriers and equipment around them. Is that something y'all are looking into in terms of using these new collaborative robots to reduce the amount of overhead in terms of space and footprint that these require?
Competitors so we're not the only player in this space. There are several robotics providers cropping up in recycling, and there are some cobot offerings on the market because usually these facilities are not zero automated to fully automated. You'll still have human sorting, but you'll put a robot in and then maybe get another robot. And so it's attractive to consider cobots for that application. Our take on it is, again, on complication of problem. It takes a lot of engineering work to make a robot safe to be next to, particularly if you also want it to go really fast and sort really efficiently. So we've gone a different direction where, okay, make it small, make it take a very little footprint, and it's still caged so that a human, in a given area, a human can still be downstream of the robot also sorting, and it doesn't preclude, you don't have to choose this or that, but it allows us to sort of sidestep a lot of technological concerns that would make it a lot more complicated to build a cobot.
Yeah. And then I actually have a friend that used to work at AMP, so I know a little bit about some of the other processes that y'all have done, but one of my favorites is the airjet based sorting with the array of pneumatic tubes under the primitive conveyor belt. What cases would you use something like that versus using a robot to sort the stream?
Actually, in most, in many cases. So okay. Any company that's trying to start out in tech, you need to provide value to an existing market as soon as you can. And so the way that we did that was with these systems that can replace human labor and make the existing facilities more effective. I mentioned at the end, well, what if you design your own facility around the robots themselves? Well, we have a lot of different robot variants. All of them use the same sensing and compute stack, and then we just have a different harvester. So if you want to drive a Delta harvester with the vision system outputs, great. If you want to drive something else, you can. And what Michael mentioned, we call it the jet. It's an example in industry. There's precedent for this. It's called an optical sorter. You have a conveyor belt of material, and the conveyor belt ends. And there's another one below it. With nothing there, the material is just going to fall off that conveyor belt and go to the next one. So it's a transfer. Well, right under the conveyor belt, you can put a bank of valves, just air valves. And if you have some sensing apparatus, you might have seen this with Apple sorting and stuff. As an object falls, if you want to sort it, blast it up. Blast it up to some higher conveyor belt and it gets conveyed away. Or if you don't want to sort it, just don't fire the valve, keep that solenoid off, and then it'll go through. The pros and cons of these two robot variants, so the Delta style is kind of meant to replace humans and be retrofittable. You don't have to change your conveyor belt layout to put one of those in. I don't need to cut this conveyor belt in half and have another one with a takeaway conveyor to install this type of robot. But it's also just going to be limited to 80 to 100 picks per minute, right? It has this limitation of recovery because it's picking and placing. On the other hand, the jet allows you to do thousands of picks per minute because all you have to do is turn a solenoid on or off. But you have more retrofit cost to put one in, or you have to design the facility around it. Both are disruptive in that they are not using, hyperspectral technology to do the sensing in the first place. It's an expensive compute system, but the RGB sensor is an RGB sensor, so it's like a couple $100. So, moral of the story is that type of robot is the core building block around which we've built our own facilities, because you have a combination of a lot of really cool things that the industry doesn't have to date, and that is one. High volume sortation, so you can do those thousands of picks per minute, and that exists today. Two, you have insane flexibility in what it can sort. Because it's RGB AI, we can change and update and improve what it is able to see and add new classifications that it can see, so that you're not locked into, I can see these chemical signatures and that's it. And as a result of those two, plus a really important third one, it's a lot cheaper. If you're not using some hyperspectral sensor to drive that, then instead of your facility design, like, hey, greenfield, I want to build a new recycling facility. Yeah, our budget means we can have like 2 of these jets with a hyperspectral camera because they're really expensive. That constraint gets relaxed because they're so much cheaper that instead of having 1 or 2 of these that you design the facility around, you have 20 of them. And so that is kind of how our facilities look, where we're using the benefits of AI and this robotic system, where the physical action is just a solenoid turning on or off, so very limited robotic control, but it is still a robot, and they can drive so much more efficiency that way.
Yeah, cool. That's an interesting consideration, like the retrofit cost. Obviously, the interesting. I'm sure lots of companies end up with a whole array of options for people that want to sort recycling based on their tolerance to, absorbing that retrofit cost. So
totally.
Yeah. Well, cool.
You talked about,
oh, go ahead.
Sorry. You talked about some of the options, the Delta versus the Jet. What do you see as the kind of the next step, right? Technology has gotten good enough. This works. What do we need next to see the next kind of step here?
In our opinion, it is using these jet robots and facilities designed around their efficiency, and with AI having far more flexible removal of more things. Up to now, a lot of the heavy equipment in facilities just uses density separation, basic physics, eddy currents and magnets and stuff like that. But if you really have the ability to see and sort, instead of into 6 commodities, into 30, then the innovation starts coming into a different question. How can we take cleanly sorted polystyrene and get value out of it? And that's the next chain in the market, right? If in our contention is if we can sort it, they will come. Yes, cheaper, more flexible, high volume robots as the building block of a whole facility. That also allows things like very small facilities that are still profitable. A lot of more rural or distant communities just don't have a recycling option because they don't have enough volume to justify it. And this would bring that down. So it market makes in that direction too. Does that answer your question though?
Yeah, absolutely. Just making it better mostly.
Yeah, just hey, you have a fundamentally more efficient Lego block. How much cooler can we build the facility out of these Lego blocks instead of the old ones?
Yeah. Cool. Well, that's all the time we have for your keynote. But Joe, thank you so much for coming on and sharing this with us. It was really fascinating to hear about, everything y'all are doing and what the industry is doing as a whole to make, recycling more efficient and more profitable. All the best of luck in the future. It'd be so cool to see this stuff become more and more widespread and just really, really help us keep as much waste out of landfills as possible. So, yeah.
Absolutely. And thank you. Very excited to join today.
Thank you for being here. All right. Well, our next presenter is Daniel with his Acrobots.
Hello.
Yes, please. So Daniel, whenever you are ready, feel free to come on and share your screen and please take over.
Just checking the right screen. I think this should be good.
We can see that.
Good. And let me minimize this Zoom thing. There we go. Hey, hello. Thanks for having me. My name is Daniel, and in this 30-minute presentation, I will tell you about my project, the Acrobots. In a moment, I'll give you an overview of the topics that I want to discuss in this talk, but first I want to give you a real quick impression of what the Acrobot is, and rather than telling you about it myself, I let me of the past do that for you. So I have a quick video over here, and it's also a test to see if sound and stuff works through Zoom, so let me know if you don't hear something. Hi, my name is Daniel Simu. I'm a circus artist and tinkerer. I like to build props in my shows, and today I'm working on Acrobotics, a robot to make a circus show with. I do an act called hand-to-hand, where I lift my partner up in the air and she does a handstand on my hands, but I don't always have a partner. The last person I work with lives in the UK. Before I work with people who live in Berlin now. So in order to find somebody to work with, I figured I transform a mannequin into a partner of my own. I'm inserting electronics like motors to make the arms rotate, and hopefully at my command we can do some tricks together and tell a story about human-robot interaction in a way that's never been done before, because what robot relies physically on a human to work together? Well, so far it's not doing much, but at least that's the plan. All right, so the Acrobot, perhaps not the kind of robotics exercise of the inverted pendulum that some of you may have expected. It's also called the Acrobot. I wasn't aware when I picked his name, but that's also named after an acrobatic robot, so it seemed to make sense. I'll be introducing myself in a second, explaining where I come from, what I'm building, why I'm building this, the kind of things I learned through building this and sharing this with the world, kind of challenge I go through, and I'm highlighting one of those challenges, which are some issues I'm having with motors. Perhaps you can even advise me on this later, and where I'm taking this into the future. Starting with, oh, and we have time for Q&A, of course. Starting with me. I am not a roboticist by trade, or at least slowly I'm becoming one, but actually I'm a trained circus artist. I was touring around for almost 15 years with various circuses, a juggler, clown, acrobat, musician, doing everything. One of the acts I was doing was, as I already said in the video, hand-to-hand. So I balance a partner on my hands and they do a handstand in it. But I was often having bad luck with the kind of partners that I had, because they would move to different countries, or I'd be the one moving. I lived in London and Toulouse and Berlin and the Netherlands, or they would get injured. So at some point I was really frustrated with not having a partner, and I figured I could just build one myself. And I came up with this genius 3-step plan to do so. Step 1 would be to buy a mannequin. If you ever go to a second-hand mannequin shop, this is what you see. I am standing there in the middle, and it's a very eerie place, being surrounded by 10,000 mannequins, but fun experience. Step 2 would be to add motors to the shoulders and the hips of the mannequin. I was going to keep stuff simple by not having knees that you can actuate, or ankles or wrists, or rotating in multiple directions. Just one single axis per limb to be able to keep the project maintainable. And I figured I can do most of acrobatics that I wanted to try with the mannequin. I could do it that way. And then step 3 was, of course, to do tricks and balance them on my hands and do things. And I pitched this plan to an art institute, V2, and they were like, yeah, sure, come try this. And I built Luca, which surprisingly somehow kind of worked. There, Luca is in the right. Am I overlaying on that? Let me remove my screen. So Luca had only 2 arms, no legs, but 2 very strong arms. You can see it doing a handstand. I'm not too sure about this. We'll talk about gender in a moment. It was remote control. So somebody was with me on the stage with a small remote that would move the arms, because there was no position feedback on the motors. I tried to build it in and I failed. So the little wire you see running, it's not the power supply, it's just the control, because also I was running out of time and didn't have time to implement some kind of wireless interface. It was very friendly, like it had a face and it had hands. And the funny thing is, I had been thinking about what kind of tricks I wanted to do with the robot for months. And the moment that she was finished, like she would reach out her hand to me, and suddenly I was like, I want to shake their hand rather than do tricks, and I want to hug it and talk to it. And that was a funny realization that only came. I became aware of that as I could finally see her, or it, for them. But yeah, it wasn't much better than my other injured human partners, because Luca would get injured too very quickly. I was in the show, like it was the third or the fourth show we were doing, and as the little motherboard had a different battery from the arms, and as I plugged in that battery, I pulled out the wires and I pushed them back in a hurry, and of course put the polarity wrong, so then I fried the motherboard chip, and then I couldn't perform. And just shortly after, I broke an arm off because I was abusing it, and now it's living in my basement as an amputee, retiree, and an organ donor, because I was so enthusiastic about the whole process. I made another robot, which I call Robin. And Robin, let's see if this video also plays. Maybe I should hide myself again. I like having my face on screen, but I think it still fits. Let's see what happens. Yeah, just about. I can keep on doing it. So Robin is the second robot that I built. It has 2 legs and no arms yet. The plan is to add arms to this, but there's so many other things to prototype first before it's worth doing that. We're doing just 2 legs for now, and it can run autonomously. Like, it can't run away from me. It's not walking because it has no, can't move its hips side by side. It has no knees, no ankles, just like the other one. But right now I don't need the human controller anymore. I have pre-programmed sequences that I can trigger, and then it does those the way that I programmed them in, of course. And it's very mobile in the sense that it's transportable. I can take the legs off, and I made this, unlike the last one, to constrain to what I can fit in a bag or in a suitcase, so I can travel around with it. I want to perform around Europe and the world, so it needs to be around. Oh, and right now on video is my favorite part. This is what the whole reason I made this thing, because I wanted the big tricks, like making the robot jump backflips. And I was so excited when this finally worked, but I spent so much time building the robot and so little time actually training with the robot. So this was one of the rare occasions where we could try new things. And Robin has already performed 15 shows, so it's been lasting much longer than the old one. It's mostly has not been broken yet. Like, this is a show that we did in Zurich, in Switzerland. But the major downside is that will cut off your finger. Like, I don't know this for sure because I haven't actually cut off my finger yet, but there are places where if you get your finger trapped, these motors are strong enough to do some damage. And by the way, on screen right now you see not me, but you see Mila performing with it. I luckily don't have to do everything myself. Behind Robin standing, we have Basti Kutz, a mechanical engineer who's been helping me with modeling a lot of stuff in 3D and making 3D prints for Robin. And Mila, she was controlling Luca in his first performance, and she was performing with Robin in second performance, and she helped me figure out tricks. Like, when you want to do acrobatics, it's often helpful to have one person holding a remote and the other person holding the robot, and then go back and forth. So I got some help. And possibly the most important partner is V2 Lab for Unstable Media in Rotterdam, in the Netherlands. They are able to give me some fundings to be able to buy parts and spend time, and also this picture is taken in their space. I'm looking to expand the team. Right now I'm talking to a programmer and an electronics engineer and a writer and a dramaturge to be able to finish the robots to a more professional level and to be able to make a proper show with it, because that's one of the goals. So why should I build the Acrobot? Of course, in the beginning it was to replace a partner, but this is no longer a good excuse. Like, I invested more time in the robot than I ever did in a human stage partner, which is saying a lot because I have been a lot on stage with human partners, but man, it takes time, especially if you have no clue what you're doing. But most importantly, or no, not necessarily most importantly, but first most, is that a word? I'm interested in movement. As a circus artist, I move on stages, and at the bottom you see a stage and you see a robot doing a split, which is very different from how I do a split. And the robot not only moves different from how I move, but also I get to move different because I'm holding a robot. And it's very interesting to try and go on stage and mimic each other's movements and see where that takes us. And I want to bring robots closer to people. Like, when I started with this, I had never met another humanoid robot. Humanoid robots are very prevalent in media and culture and movies and series, but we don't actually see them. So we have a lot of, possibly the general audience has misconceptions about what they are and what they can do. And it feels very different to talk about a robot, to see the robot on screen, when compared to when you meet one in real life, especially one that's larger than your average Roomba. And then ultimately, I want to start a discussion about technology. I am a self-taught robot builder, and I didn't know 3 years ago that this was even possible, that you could learn this stuff online on YouTube and buy parts for your, well, I started out with like Arduino parts, and that is very accessible. So I want to help other people become aware that it's accessible by making a robot that is mostly translucent, that has relatively simple parts so I can explain them. I don't want to mystify it. I want to be able to, anybody who has questions can come up and get a straight answer about how stuff works. Maybe in the show, I'll play with the mystification for a moment, see if I can pretend that I'm giving control away to the robot. But at the end, I always want to bring back to a real world scenario where people understand that it's something that is in my control. And here at the top, I was speaking at the Dutch Innovation Days, for example, about what it's like owning a robot acrobat. And I would like to understand circus better. So I'm a circus artist. Circus has been going through this huge transformation over the last 20, 30 years, where it goes from just showcasing tricks to telling a story through those tricks. But tricks are still the very core of what we circus artists do. They're what make us different from, for example, a dancer or a theater performer. And tricks are this thing about human achievement and success and hope and challenge. And do those kind of things play? Are they valid topics for robots? Should we applaud a robot that does a backflip, or do we applaud the author, in this case me, who made it do a backflip? But I think that these are interesting ways to try and redefine what circus is today, or to try and understand how we look at tricks and what it has to do with our sense of whether a human is important in doing those things or not. And last but not least, maybe this is actually the most important. It's my job to go on stage and do something interesting, and I like making stuff interesting for myself as well. And for me, the idea that I can make a robot do a backflip is insane. So that's what keeps me, what drives me to make this. And I hope that the people watching this, or the people watching my performance, will also think that a robot doing a backflip or a robot doing a handstand on me is a cool thing worth watching and is to some degree entertaining. So I've been showing the robot around a fair bit already, and the biggest thing I've run into that I had a tough time dealing with, or still do actually, is this kind of anthropomorphization. Like, I experienced it myself when I was shaking hands with Luca, the first robot. You see this robot as another person. There's no way to avoid giving some kind of identity to it. And when I started building the first one, everybody was asking me, oh, what's its name? And for the longest time, I didn't want to give it a name. Like in the first shows, it did not yet have a name, because I was worried that by giving it a name, I would somehow taint it, that it would no longer be able to be colored later in the kind of show that I wanted to make. I didn't know yet what the kind of show I wanted to make was. I just had a mechanical object. And if you have a robotic arm or a Roomba, you don't necessarily need to give it a name. Why did I need to give my machine a name just because it had human-looking hands and a face? But it turns out that it did need a name. But then as soon as it had a name, then it needs a gender, because like I was already saying, it's like he is doing this or she's doing that. And do I need to be consistent with that? And do I care? And all these questions about character arise. And people also ask me, like, what's its age? And there has been a show where a robot has been talking on stage using my voice that I pre-recorded, which meant that it had a Dutch English accent. And yeah, that asked a question about the nationality and origins and all these kind of things I didn't necessarily want to get into, but just by making a humanoid robot, I can't avoid these kind of questions. Also, I get a lot of questions about AI from audience, and I am not an AI expert. I'm not qualified to talk about this, but ChatGPT and image generation are topics that are very are discussed a lot these days. And seeing a robot that does some things that look to some degree magical to people, there's no AI in this whatsoever. Like, it's just a motor on a PID loop where I say the set point, and we'll go there, and then we'll go back on another time frame. But seeing a robot makes people come up to me like, oh, what do you think about ChatGPT? And will it take over the world? And will your robot take over the world? And where do you see the future going? And this kind of things, I guess I need to become an expert at now, because it's unavoidable that I need to discuss these kind of topics with audiences that come up to me and the robot with interesting questions. The expectations of what to do with a robot on stage differ a lot from whether I'm at a technology-centered event or whether I'm at a circus-centered event. At the technology events, I noticed there's a really low standard for artistic artistic exploration or artistic expression, or especially performances. Like I'm a professional performance artist. I studied at a circus school for 4 years. I've watched probably 1,000 shows in my lifetime, so I know what a good show looks like, and I have high standards for what I want to do myself. But at these performance events, if you just so much as make yourself slightly visible, people are already excited that there's somebody on stage. It's so unusual that the author of the mechanic is also part of the presentation of the mechanic. Whereas at the circus shows, the circus people that I met with the robots, they are very much opposite. They care a lot about what the show is like, and when they ask me about what the characters of the robot and what my role is and why I didn't make this choice about what I do with my body next to the robot. But on the other hand, they have zero interest in the technology of it. They don't care if I say, like, oh yeah, it's just 2 motors, or to them it's all one big mechanical blob of them, just like your phone. Like it works, and they expect it to work, and they have no measure of how much work would have gone into making this, or how I would design it, or to them it would probably make very little difference when I had bought this robot or when I make it myself. Where to me it's a big part that I invest myself into making this robot, and I'm the author on stage. And then this whole thing with the head, like on the top picture, there is no head on the robot, and on the bottom picture there is. And I've performed with both versions. And when you have a head, people say like, "Ah, without head would be a pity." And when you have no head, and then people say like, "Oh, with a head looks kind of weird." So I was still searching to what I want to do, what I'm going for. But yeah, so far I think it's going towards that when it has a head, people have higher expectations. People ask, where are the hands? Why are there no hands on this thing? And people wonder about, does it have a voice? Where does it come from? Whereas without the head, it's a bit simpler. People see it more as a walking machine. Whereas the head does nothing. Like I use the legs or the feet, and in the future of the hands to operate the robot. Like I want to do tricks with it. But the head is just there for aesthetics. It's kind of pointless from a mechanical point of view. So it's interesting to me that it's such a trivial thing for the performance, even though for the robots it's kind of useless. The kind of challenges that you have with the performing robots, different than from other robots, are that it needs to be super reliable, like show must go on. When I'm injured and I can only do, let's say, 50% of my show, I can still do 50% of my show, and I might still show up and do something. Whereas a robot is more binary, like it will go on or it will go up. And if I fry the motherboard like I already did once, there's no show and there's nothing I can do on stage. And it needs to work night after night after night. Every single time that I want to go on stage, I need to have a show ready. Otherwise, I can't sell this thing. It's very, very, very disappointing to have an act ready that doesn't come on stage. It needs to be also robust in the sense that it needs to be strong. It's going to be handled rough. Like backstages are dark and people might stumble over parts, or I might take the robot outdoors, or there's loads of spaces where I take this robot that are not designed for robotics. They're not necessarily clean rooms. It needs to be scratch proof, and it might be handled by other people than myself. And of course, it needs to be transportable, like I already mentioned before. So the first robot was a big block that I could not take apart, whereas a new robot has is fitted to bags and needs to be easy to fix. So when I need to replace parts, I might need to do so whilst I'm on tour, so I can't have access to a drill press or something. It needs to be with little hand tools I can carry around. I should be able to swap out parts if I would need to. The biggest challenge of my life has been the motor. Oh, what's this video? Ah, yeah. This video is the kind of goal that I set myself. I wanted the robot to be strong enough to do a planche into handstand. So there's an acrobat doing this kind of thing. I figured if a human can do it, my robot could do it too. And the robot is, of course, much lighter than the human. And I calculated that with the kind of weight I expected the robot to have, I needed motors that had 20 newton meters of torque and could spin around 60 revolutions per minute. That's seemed to be like what I could do with my own hand and what I wanted to use in the show. It needed to be encoded. Like I needed to know the position of the motor, so I need to add some kind of absent encoder on it. It needs to fit in a very limited space, especially between two hips. There is almost no space. You can look at your own hips and take the middle of your leg and then figure out how much space there's left to fit in two motors back to back. That's not a lot. And these motors, they're designed to spin around, but not to have load in all kinds of odd angles, which I might also potentially put in the robot. Like there's a meter long leg on this thing. If I push that slightly inwards and the axis breaks off, that would be a terrible problem. And you can have a motor that's strong enough, but if you can't couple it to something else that's also strong, it's really hard to find couplers off the shelf that can support 20 newton meters of torque. I discovered, like, that's not the kind of thing that you buy on the internet. Like the golden standard supposedly is to cut a groove with a mill into an axis and to fit a little key in there. But that requires you to have a mill, or it requires you to have the square scrapey thingy, which I forget the name right now, which I don't have. And you can buy them at pre-made sizes, but never the size that you actually need, of course. And if I want to adjust anything, it needs to be doable with DIY tools. So I looked into a few solutions to get this kind of torque. You can have a big motor and then have it reduced with a belt gear thingy, police thingy. But to get the kind of reduction I needed, you probably need multiple pulleys going back and forth. And this takes up a lot of space, which I didn't have. And also to design that, I probably need to be a better engineer than I am. So that was not a good idea. A possible solution is to use kind of pancake motors with a harmonic drive inside. They seem to be pretty great. They are designed for robotics, so probably suit my need. But they are also at least 500 to 600 euros each, and I need 4 of them. And right now, I can't afford to, like, if I know for certain that they will be the answer to my problem, I might be able to buy them. But I can't afford to just test them and then break one and then have 2,000 euros wasted in 4 motor arms, so arm motors. So if you are an expert on these kind of things, do get in touch, because I'd love to know more about them. But now I settled for wiper motors because they're ridiculously inexpensive and have about 25 newton meters of torque. They have a worm wheel inside, which brings them to a kind of speed of 60 RPM, which is perfect. And I pay 30 euros each for these motors. Sadly, it's not all great. I mounted an encoder on the back, which makes them suitable for me. But they have this PLA gear inside, the wheel, as we call it. And I've had wheels where I get the tooth stripped off, and I've had wheels where I had the axes come loose from the wheel. You see that's on the first second picture. I actually have the video right here of the moment where I managed to break both wheels in one show. Yeah, this is supposed to be a chaotic moment in the show, but already I see that it's. I did the show already 15 times, and then this was the last show that I did. Actually, the last trick in the last show that I did, which was perfect timing for them to break, and they both break at the same time. Let's see if I can skip to that moment. Oh no, it's already going to another slide. I want to give it a shot. Let's go back. Is it going to load the video again? It was such a strange coincidence. It's a bit funny because I can't use my normal YouTube hotkeys in this presentation. And I will skip through it. Give me one more chance. All right, so the robot's kicking up full force here. Is this not working? No, it seems to not want to skip frame by frame anymore. Never mind. And it's kicking full force, and one motor gets stuck, and then it does one more kick, and then the other motor gets stuck too, which is. There's one motor stuck, and now the other one is stuck at the top. So yeah, they both break, and this will keep on happening. Like, it's not a bad thing if they break once every 15 shows, except that I can't predict it. So I need to. How do I exit this again? No, it's not working. It needs to be predictable, so I can have this ultimate reliability that I want and need, and it's not. So I need to find a solution for that. I'm looking for stronger motors again, but funny enough, these wiper motors, they cost 30 euros each. One step up from them that are slightly more torquey. They're not made for automotive solutions anymore, so suddenly they cost 200 to 300 to 400 euros each. And again, I don't know if those will fail too at some points. So that's the problem I'm having. If you have advice on this, do get in touch anyway. In the future, I need, of course, to add arms, but before I add arms, I redo all the electronics and redesign the frame for it to be more safe. We have some plans for that. And I found this amazing software, Botango. It's made for animatronics. You see it demonstrated here. It's you can animate your robot in them, and then it generates code for your robot. We have to modify it a little bit because we don't want code. We just want the output values. But it's animation software for animatronics that we intend to use. And of course, create a performance. Like now, I made some rushed demonstrations in like 2 or 3 days. But ultimately, I want to go into the studio for a month or two, like you would do with any theater performance, and go figure out what you could do on stage for half an hour. And I have some ideas about this. I just need to get some funding for that. So I'm looking for income really hard at the moment and finding some partners who want to invest in this project to be able to make it real and go on stage. Because like many other art projects, it's not self-sustainable, far from yet. So that was my presentation, and I think we still have some time left for questions. So please, if there are any, feel free to bump in. And in the meanwhile, find me on Instagram. I post on YouTube some progress stuff, like the kind of problems I run into, and I share them there, and or share the stuff that I learn. And yeah, that's about it. Thank you for listening.
Yeah, fantastic stuff. Like we said in this morning's presentation, we really love seeing artistic robots, like this. It's just a really cool take on robotics as a whole, and it's really fun seeing people come at the discipline from an artistic state of mind.
Yeah, your comments about the expectations per audience really that tracks with us, because like every time we have an artist come and like show that they've learned kind of from scratch all these things, I'm super impressed, because I'm not at all on that side. I've slowly worked through all the engineering, and then the aesthetics are kind of secondary. So really cool to see that other perspective, and I suppose that makes me an easier audience to impress on that side.
Yeah, I mean, so just one question right off the bat is, where do you see this going next in terms of levels of complexity? You've talked about it being remote controlled. You've talked about it having pre-programmed, movements. Is there any room in the future in your head for any kind of more complicated control system where it's, has maybe an accelerometer, it's trying to balance itself, anything like that?
Yeah, so mechanically, I set myself a very clear constraint, which is just to have 4 actuators inside. I want to keep it that way, both for aesthetic reasons and for complexity reasons. But on the control side, there is an accelerometer inside that I'm not utilizing. I would love to use the accelerometer as an interface. When I work with a human partner, we agree beforehand on what kind of move we're going to do. But then in the moment of doing that move, we communicate by pushing and pulling on each other. Like that's how we give a tempo, and we know the moment that we jump. I want to have this kind of same communication with the robot, so that it can sense where I'm going. And perhaps I can even operate it as a kind of like a menu that I can select different moves, and depending on whether I make it turn to the left or whether I make it to the right, it will do a different kind of step that I preset, so I can improvise with the robot. That's a really nice goal that I have, but so far there's so many other hurdles that will come before that I can't really dive into that. I wish that the mechanics would all be solved, because I think that the interfacing and controlling is much more interesting, but it's kind of can only be done one at a time, and the mechanics is the one that is stopping all the others from progressing.
Yeah, absolutely. That's a very interesting take on what you're going to do next, and it's interesting because I agree. I think 4 motors is a great place to start because it gives you the humanoid motion, but at a very low level of complexity. So I totally get why you're sticking with that and working more on the software control side. Someone did ask, will you add more, silicon to it or anything? Like, will you add more kind of meat to it to make it look more human while keeping that kind of transparent view that you want to maintain?
So when I started out, I was actually thinking to like get some foam covers to make it nice to hold as well, and to then dress it up, like give it a shirt and some trousers. But the more I started working with it, the more I started to appreciate the mechanical look of it and the rawness of it, and also being able to, it makes it much easier to invite others to look at it. I will actually be working with silicone because right now it doesn't have hands. The previous hands, they are these mannequin hands, and the wrist doesn't align with the direction that it needed to be. And also it's really hard to find these kind of open hands that I need for my handstand kind of grip. So I want to create my own hands by casting them for silicone and having some kind of solid core inside, which is another project that's going to take me 2 weeks because I have never done that kind of thing. There's all these hurdles that they sound nice on paper, but if you've never done that, you're going to run into problems. And so yeah, but no, I'm not going to cover the whole robot, at least not for now. But maybe if we end up in the theater and we are making the show and figure out like, it would be actually really nice to dress it up some more, maybe we'll add some covers, but it could be very basic, like perhaps also isolation for your radiator pipes, like these kind of foam things. We might be able to click on to the current pipes, that kind of thing.
Absolutely. Yeah, no, it's so cool to hear your thought process about, how you expect the audience to respond to the robot, what that interaction looks like, and how you're kind of forming that with making it look more mechanical, more robotic versus more humanoid. I think that's really fascinating. Well, I think we're coming up on the end of our time. Thank you so much for presenting, and we hope you maintain any sort of activity in the subreddit or the Discord, because I'm sure people would love to see where you go with this, but also would love to help with any technical questions or technical expertise that you're looking for on the engineering side of things. So with that, thank you, Daniel, and we'll move on to our next presentation.
Thank you. Goodbye.
So our next presenter is Luis, and he will be presenting Zeus 2Q, his humanoid robotic platform. So Luis, are you ready to present? Oh, I think you're muted. Luis, can you hear us? Oh, there we go.
All right. So I'm going to be doing a live presentation on the robot. This is Zeus 2Q. So my name is Luis Guzman. I am the owner and CEO of System Technology Works. I've been working on this robot design for about 6 years. The company just launched it 2 years ago, trying to bring humanoid robots to education. So I'm going to have the robot do most of the presentation instead of me having to talk.
Initializing system, now give me a second. Hello humans. My name is Zeus, and I'm here on the behalf of humanoid robots. I was designed for research and STEM education. I have simple parts. Wait, what are the parts I forgot? Let me think. Oh, okay, I remember I have servo motors and lot of wires. And remember a controller board and a video camera so I can see you and measure your distance. I might have a sound card with a microphone, so be careful, I can be listening to everything you say. I think there is a computer to help me remember and process information. I wonder if the computer is working because I cannot remember anything. Okay, I think I need a reboot. Give me a second. I am back. Let's do a role play. Use 2Q Jedi mode. My Jedi senses.
So the Jedi senses are
Do not sense anyone close to me.
actually using the camera. So
Stand back.
when you send somebody,
Only assist deals in absolutes. My Jedi senses. Do not sense anyone close to me.
you're close to you.
Let's play rock, paper, scissors.
All right.
Rock. Paper. Scissors.
Shoot.
Shoot. Rock. Good game next.
All right. So let's go next. Let's go to the AI presentation where,
Let's start a conversation.
all right, let's have a conversation then.
Ask me
Okay. So how have you been doing today? Are you listening to me, Zeus?
Yes, I am a good listener.
You're a good listener. That sounds great. That is awesome. So,
Yes, I am a good listener.
okay.
So,
Yes, we're not going to get into a debate here in camera, so I'm going
what
to,
do you really want to ask me?
not in camera. So we are going to pause you for a second, and then we are going to answer any questions that we have right now. So we're going to go through Z. So his design and built. We have built a robot with IntelliSense cameras, be able to capture floating points. We're using Jetson Nano as the computer for this robot. We have a custom board microcontroller that we're using to actually control all the servos. These are standard Howdy servos. We're using a reed microphone array and sound card to be able to listen to the sound and also for the speaker output. So most of it, the battery is a nickel halide 7.2 volt battery. We're using 2 of those. They last about 4 hours. So that's pretty much. He's capable of walking. I was trying to get him to do it for the presentation, but I did not get the time to get that through. That's what we got. Any questions?
Yeah, great.
It's fantastic stuff.
Yeah,
Yeah,
not
so I
being able to
thought-
walk is not a big deal. A live presentation is a hard thing to do.
Absolutely, yeah.
Switch the audio.
Oh yeah, of course.
Okay.
One question that I've got is, what kind of motors are you using? You know, the arm movements look really good. Are those just normal off-the-shelf servos, or are you using some kind of special, motors that you made yourself?
Actually, these are standard servos. These are, I'm using the ES3225s on the arms.
Okay. Nice, yeah.
So, and for the legs, we are using the SD5160.
Great, yeah. So someone asked in the chat, are these pre-recorded, kind of pre-generated statements that it's saying, or is it connected to some kind of online server that's giving it the speaking ability in real time?
For the first session where he started presenting, he's presents himself and that's pre-record, that's pre-set. So he's actually just reading and synthesizing the text. For the last session, it's actually using AIML. So we have AIML libraries in the robot for 50,000 answers and questions.
Nice. Okay. I see that you have some other robots kind of in the background there. Is this version 3 of Zeus? And like if this is a kind of
This is the commercial version, final version. The first one over there, the one with spikes, that's the original prototype. And this is the one that you see right now that is doing the presentation is the first production run. Has some issues, but corrected those and already started producing 10 more units.
nice. Yeah. I mean, what problems did you have with the earlier versions that you solved in this current production version?
So it was, measurements and stuff like that, that as they went through, production, it's no longer, some drawings got to be adjusted and stuff like that for better manufacturing, because as you first build your prototype, it's not really the same as when you're building on volume. It's just, there are things, compromises that you have to make and adjustments when you are building in volume.
Absolutely. Yeah. What use cases do you see for this? Can it pick up and interact with objects, or is it mostly kind of a human interaction kind of robot?
So my view of this is the ideal STEM robot, because you got hands, you got cameras, you got voice, so you have all the components that you will need in a robot for education. So this is my goal is more STEM education and kind of competitions, robotic competitions.
So with regards to education, I assume it's got libraries and that you can code it to do whatever you want. There's some customizability there.
Yes, right. Since I have basic libraries in Python, but it's fully open to customize however you want to customize it. Right now it's just an NVIDIA Jetson Nano in that one. The one behind me over there has a Savior. So you could put, and it doesn't have to be an NVIDIA computer. You could put a Raspberry Pi or an upboard, whichever computer you feel like connecting to it to do the processing. You just connect it to the microcontroller board, and you're able to communicate with it over serial port.
What microcontroller is it using for the motor control and stuff?
What we've done is we taken the one of the microcontroller. Hold on a second. Turn this puppy around. So what we've done here is we have adjusted all the power and everything to work, and this is the I'm drawing a blank. Forgive me for that. Really? Can't believe it. Right now, I just can't remember.
That's not a
That's all
problem.
good.
You can follow up after the presentation if you remember.
Yeah, of course. Is it something like an Arduino or an ESP32 or anything like that?
It's not an Arduino because I actually started with Arduino, and Arduino because I need to be able to control all servos at once for movements of the hands and everything. And with Arduino, it's kind of a little complicated to do that, multi-processing. So right now, give me a second. Sorry.
Yeah, of course, no worries.
There we go. So this is the Maestro. Like for the life of me, couldn't remember. Maestro, made by Palulu.
Got it. Yeah, that's a great platform.
You're using two of those, one to control the legs and one to control the arms. And all the commands are sent over Python over serial. And it works pretty well with once you configure and have all the electronics connected. So right now the next stage is more making him more dynamic, being able to just walk around the office and chat, more command based, so you could just with the Python and With the text-to-speech, you could do a lot of more command-based commands, so that you just tell them what you want them to do. So
Got it. Yeah, very cool. So one last question. If this is meant to be more of an education product, how much would one of these cost?
So right now, the cost, I'm looking at a basic robot without, additional installation is $6,000.
Okay. Yeah. That sounds great. All right, cool. That's the end of the time we have for this presentation. Luis, thank you so much for your presentation. I really appreciate your time. It's been great to see, your whole process with making this really cool humanoid product, and we hope to see more of it in the future.
All right. Thank you. Thank you for having me.
Of course. Our next presenter is Kishit Tiwari, who appears to not be in the call right now. So, Chris, would you mind seeing if you can hunt him down and get him on?
Yeah, for now, we should probably go to the next presentation.
Yes, yeah. In the meantime, Sayak, are you ready to present?
Hey, hi. I'm here.
Okay, well, Sayak, sorry to make you go a little bit early. I hope that's okay. But if
Yeah,
you
sure.
are ready to go, please share your screen and the floor is yours.
Sure, I'll begin. All right. I hope my screen's visible.
We cannot see your screen right now.
Is it on?
We can see a video view, but not your screen.
Oh, sorry. It should be on by now.
We still cannot see. Let's see. Let me try an exit full screen. There we go.
Yeah, I can see it now.
All right.
There we go. Now we're good. All right.
Good. So, hi everyone. Thanks for having me here. I present to you a web-based robotics. This has been a project which I've been working on for quite some time. And my main aim over here is to export ROS robots as a web application using various web stack and resources available in open source. So these are the brief overview of the contents which I'll be going through. Firstly, I'll be going with introduction, personal introduction, and the motivation about how I came up with this project. A brief overview of what has been done and what I'm going to do. A more systematic view over the problem statement, whatever I have in mind, which I want to implement. Targets, where I have broken down this into a few phases, and there I'll be explaining the components as well. So I'll also be explaining about the current developments in the space and going over the few reference materials. After that, we'll have the Q&A time. Moving along, an introduction and where my motivation comes from. So I graduated from mechanical engineering, did my bachelor's in NIT Karnataka. So I did my bachelor's in mechanical engineering and my minors from electrical and electronics and communications engineering. I was always interested in hardware, and I always wanted to go into design of machines and like the development of systems which are able to interact with the world. I was always invested in coding as well, but some part of me always wanted to see my code manifest itself into the physical reality instead of just executing on the screen. So here I have a picture which is like very near and dear to my heart. So this is where, so I got introduced into the entire scene of robotics through a competition called RoboCon. It's hosted by ABU, Asia Pacific Broadcasting Unit. So this was the room where my college team used to prepare the robots, and this is where I learned I started my entire robotics journey, and I started learning about robots. And that is where my motivation stems from. So I learned a lot from my seniors. And during the entire COVID lockdown of 2020, I was in my second year and I really wanted to get into the robotic space. But unfortunately, we had to go back to our homes and there was not any way to access hardware. So all we had was software resources available to us. I scoured through whatever online resources were available, and I came across ROS. ROS seems to be a very, very nice framework and a very extensive framework which has a very large support base. And honestly, coming from a non-coding background, it was initially very difficult for me to get through it, but eventually I was able to navigate through ROS, and I'm pretty glad that I did. But I also realized that there was a very high initial setup required, a lot of things which were required at that time. ROS 1 was like there was no ROS 2. That like ROS 2 was just coming up, and ROS Melodic was on the rise. And it was very difficult to coordinate with people who were in part of my college group. And I wanted to teach them about robotics as well, not just theory, but also practice. But the only resources which were available to us were simulations. So I came up with an idea that what if we take our simulations, whatever I'm able to do on ROS using Gazebo, and I'm able to put that on a web page. A web page is something which nobody needs to set up. They can view it whenever they want, and they will also be able to learn what I am teaching them through and be able to move the robots on their own and try to innovate on the by themselves on the robots which I'm presenting. So this is how I came up with this idea. A brief overview of the project. What I aim to achieve through this project is first was getting a simulation on a web page. So I use my laptop as a host, and I'm running a ROS simulation on Gazebo, and it's using a GZ client called as GZ Web, and I'm sending it commands through a web page using the library called ROSLibJS. So I had mainly created this for academic purposes, but I also later on figured out that what if I can function it as a product in the future, where people who are creating such robots, they need to demonstrate it to their clients. And if they want to demonstrate a simulation and make it interactive for the clients as well, they can basically port it onto a web page, and the clients can access them very easily instead of having to set up entire ROS on their own systems. I split up the problem statement into like 5 steps over here. First was to get the visualization onto the web pages, and then design low-level controllers for them. The first controllers would be just moving left, right, up, and down. Then my plan was to go about on a joystick, a virtual joystick. Then so once the functions were properly exposed, I wanted to make it the robot as a proper package and create an inline editor onto the web page so that the web page we can type out in a code language which like we can create our own code and then execute it on the robot parallelly, and we can we can see the output of the simulation right in front of us. So that was my initial plan, and I also wanted to I also want to include physical robots into this architecture. So phase 0 was basically just to visualize the basic robot onto the web. The biggest problems which I faced during this phase was that GZ Web as a library, for in between, I think a lot of dependencies were they had gone out of service and out of support, and the node version 8 was being used by GZ Web when version 14 was what was used at that time. So porting all of the libraries and coming up to a stage where the library itself is getting built was the primary issue. Secondly, I wanted it to be certain in such a way that if my laptop at that time, my laptop was in a very bad shape, so I wanted to switch systems as well. So I also wanted to import my architecture, like whatever I have set up, in a proper way. So I was trying to Dockerize it as well. Now coming to the proper diagrammatic breakdown of all the phases. So resolve for warnings of the phase 0. Initially, the models weren't loading in GZ Web. Then I realized it was an issue of paths. So the file systems, the way Gazebo accesses it is a bit different from what GZ Web was accessing it. So I think the docs need to be updated a bit. Coming to phase 2, I wanted to actually interface a real robot. And then coming to phase 3, I want to have multiple robots connected over the web, over a network. and I allow users to go like get a time slot in that, and they can do their tests on those robots through APIs which I can have exposed over the web. So this calls in for a demonstration. I will here I have my robot already set up. This is one of the mobile robots which I'm working with. So this entire framework you see over here is built on GZ Web. Here we have all of the basic world options as is available on Gazebo as well. So here is the model tree. This is my differential drive. I have the links over here and the joints. And we can also add certain shapes, buildings, furnitures. Here I don't have the thumbnails loaded because it was taking too long and the web page was becoming very slow. So I just decided not to, like in general, not to load the thumbnails. And there's another problem which is happening that when I load the furniture, the simulation actually stops. So I will not do that right now. But in general, the obstacles should be loaded, and there is a LiDAR sensor loaded onto the robot, and it should be able to detect it. Now I also have another basic web page setup over here. This is a joystick, a simple joystick. And this is what I'm using to send commands to the web page. So here we have front, back, and this is for the basic twist commands we can send over the web page. So my entire plan was to have such a host set up. And what it's basically doing is it's just sending velocity commands, which is X, certain X and a certain rotational velocity along the Z axis. So this is because of the the robot being allowed to send commands like raw geometry message commands over the web page. Now, what my intention was to have an editor over here, and I can write a code, probably put the robot in a maze, and let the users navigate through whatever way they want, use the sensors whatever way they want. That would be a very good learning experience for everyone who is trying to learn robotics, but they still haven't gotten into the entire scenario of ROS. So that is one of my things which I want to implement right now, and I have just started on it. Currently, this entire thing has been set up and I have the Docker files ready. So if anyone wants to implement this, even though it's a very rudimentary setup, if they want to implement it, they can. Going back to the presentation. So in the demonstration, I actually had a lot of, I have here my very basic things. I had put up buttons. So here, this is the time when GZ Web, which actually used to load all the obstacles. So I had a few buttons over here, forward, backward, left, and right. That is what I was using at first to send in the commands. Now I have a joystick to do that. Moving on. Okay. Yeah. So I also came across this wonderful website called webviz.io by Foxglove Studios. They basically they subscribe to a WebSocket and the exposed WebSocket, and they used and it would read all of the topics which were exposed by the ROS master. So about that setup, I have 4 things running over here. I will explain it in one bit. And yeah, okay. So I have the ROS running over here, the ROS nodes. The entire simulation is running over here. The web page, so the WebSocket server is also running here. I have the localhost server here, which is hosting my web page to give the joystick command. And this is the place where I am hosting the GZ web. This is the GZ client. So this is what you see here is a heartbeat message. So it's publishing every every 10 seconds interval. Getting back to my presentation. Oops, sorry.
Hey, just letting you know, we're getting to the end of our time. Because
All
we
right.
asked you to go a little bit early, I'm going to give you a few more minutes to
Sure.
finish.
Yeah, I'm sorry about that. So
no
I'll
worries, no
quickly
worries.
I'll quickly manage to wrap up. So in this slideshow, I have, here I actually wanted to show you how the thing was activated. The webviz.io this is how it's subscribing to all of the topics over here. And basically in this panel, you can also visualize your topic like LiDAR functions, whatever point cloud image it was getting over there. So this was the basic about what I had explained on the buttons. And this was about me trying to enforce a Python editor on that. Python is what I've written over here. It could be any language. And in my goal to interface with real robots, I also want to set up a hardware over here. So like due to the lack of resources, I'm not able to do that yet, but surely in the future, I'm aiming to do that. And yeah, coming back to my multiple robots on the web. So this is my entire pipeline, which I had set up for adding multiple robots to the web, to the pipeline here, sorry. Cool. And another diagram to show showcase the robot management system setup. Right. So coming to the current developments, I think everybody knows about the construct, and they have a wonderful setup like this, but they go into a bit more deeper, setting up virtual machines. And for like, they give the entire raw setup to give from like basic lessons from ground up to very complicated things. Currently, Gazebo, Gazebo Web 2 was also created. I came across it like 2 weeks before. I think the newer version of GZ Web is also being created right now. Cruise Automation is a self-driving company which owns which started this webviz.io. And yep, these are the papers I took into reference. That brings my presentation to the end. If I am open to questions, if anybody has any.
Wonderful. Yeah, no, thank you for such a great presentation, and thank you for such a great product as well to use. I mean, we really like web visualization. It's really nice for compatibility reasons, and yeah, it's just super cool that you've created this and shared with the community.
Thanks a lot.
Yeah. We don't have a ton of time for Q&A.
Sure.
But we do just have people saying in the chat that they think it's a cool presentation and that they can't wait to use it on their own robotic stuff. So we look forward to more development and seeing more stuff from you in the future. So thank you very much, Zach.
Thanks for having me here. I had a wonderful time. Thanks to the hosts. Sure, I'm grateful that people are willing to implement this, and I'll try my best to implement more onto this. Yeah, thanks.
Great. Yeah. All right. Well, on that note, let's move on to our next presenter. So Kshitij, are you on?
Yeah, I'm here.
Okay. Feel free to start presenting whenever you're ready and go on ahead.
Could you confirm if you see my screen?
Yes, we can see your screen.
Okay, awesome. Then just a second. Full screen. Okay, fair enough. Right. So hello, everyone. My name is Kshitij, and I'm a postdoctoral research fellow. Today, I'll be presenting about the state of robotic touch sensing and the scope beyond grasping and prehensile manipulation in the context of mobile robots. So my presentation is structured as follows, where I'll be first touching base on why I'm looking into touch sensing and what can we do with touch sensing specifically in the context of navigation. Then I'll explain the motivation of whiskers, which is where I first learned about how in nature touch sensing has been used for navigation beyond just grasping and manipulation. I'll discuss the research scope so as to motivate some of you, even builders and startups folks, to kind of look into this sensing modality beyond just the commercial off-the-shelf sensors that we have around us. And I'll discuss why currently we are struggling with the adoption of this as a widespread technology and what could it lead to in the future. So first things first, why touch sensing? So when I say touch sensing, the first thing that comes to mind is things like, single touch, multi-touch on a screen like an HCI or robotic grippers or even dual grippers. Then there is also a possibility to interpret texture, temperature, mass, and you can even use this as a measure of distance between your middle finger and your elbow as kind of like a standardized metric of distance if you don't have a measuring tape. You can also experience pressure, pain, whether something is wet or dry, or whether something stretches or not. So there's flexibility and stuff. In nature, however, there's a lot more to touch sensing than just these kind of sensor feedback. So what we'll discuss is about two possible classes. So one is, let's say, look into the whiskers of the pinnipeds, and one is to look into whiskers of the rodents. So amongst rodents, let's look at the rats first. All rodents use their whiskers slightly differently, but the ones of the rats are the ones that fascinated me the most. They are the most sophisticated whiskers that I know of. And each of these individual whiskers is independently controlled. So there is an area in the brain which it maps to. It's like a one-to-one whisker to the brain cell mapping. And they can individually move each of their whiskers around, and they are clustered all around their snout. And the rats have a very coarse visual system. So even if when they navigate in the dark and damp tunnels and stuff, so they use their whiskers to first get a sense of what they're touching, and then they use their paws to interact with it. So this is very fascinating for me because whisker contact, you could imagine it as a sparse point cloud. So they can interpret, okay, what the object is and whether or not it is safe to manipulate or interact further. Pinnipeds, on the other hand, use something similar as well. It's just that they are instead more used for like pre-contact sensing. So rats actually make a contact and then sense what did they touch. Pinnipeds, they use this whisker sensors as a modality to detect the wake left behind by the prey. So even several minutes after the prey has passed, they could still use their whiskers to detect the wakes. And the thing is, they are undulated whiskers. They have like bumpy surfaces. So it cancels out the internal vibrations that the pinniped would pick up, because the pinniped will also be swimming in the water. So they cancel their own vibrations and they only attract the vibrations from left behind by the prey. So this is a very ingenious design we have in nature from two classes of mammals. And then there are also in fishes. So there is this lateral line system that goes along in the fishes that allows for pre-contact sensing. So it's the same on both sides. And they use this to detect the difference in water pressure on either side to figure out, okay, whether one or the other, either to the right or to the left, was there an object or a prey approaching or leaving. So the difference in water pressure tells them that. So even if when they're swimming in murky waters or deep waters where the sunlight doesn't even reach, they could measure this by manipulating the response from their hair cells and the nerve follicles that detect the pressure differences. So what does that tell us? That you can even build a similar sensor for a mobile robot, and then you can use it for navigation. So for instance, there is this work from colleagues in England, and what they did was, instead of building an actual whisker, they simply used a coil spring, and it's conical in shape to represent some sort of tapering of a whisker. They placed a permanent neodymium magnet on this whisker, or let's call it a whisker. It's a spring, but it does have the same purpose. And they mounted on a base, and they stuck it as a vertical antenna on a mobile robot, and then they made it move around on different surfaces like a cobbled street, tiled street, and so on and so forth. What they did was they picked up vibrations from this whisker and they fed it to a reservoir computer, and this can help classify which surface is the robot operating on. And this is a very cool thing, because if instead you wanted to use the same thing, you could easily do it with a camera as well. But the problem is, with the environmental changes, the visual feedback would be affected quite significantly. This is immune to any such kind of changes in the environment. Another interesting application of touch sensing came up in this paper from colleagues in Prague. What they did was they had a regular Intel camera, RGBD, and then they added a bumper sensor to this hexapod robot. With just the camera, when there was this sort of like a curtain partitioning parts of the room, like imagine you have curtains in your home, the camera saw this as an impenetrable obstacle. But when the bumper sensor tried to touch it, it realized that it's a very light obstacle, and the robot is able to push through it, thereby allowing the robot to figure out, okay, wait, there are some obstacles that are technically penetrable, and you have much more area that you can actually cover than what appears to be a visually perceived obstacle. So imagine like the robot would just be cordoned off because the camera thinks there are certain areas which are not reachable. But if you have like empty cardboard boxes or some lightweight obstacles, that the robot could just move out of the way, clear the path, and keep moving. So these are the kind of things that you could only get from touch feedback. Just vision doesn't help you do that. Then there are neuroscientists who are interested in, rat has been sort of like a guinea pig of sorts to understand social interactions, and especially a lot of neural processing in the neural pathways of the brain. But the problem is, if you want to understand how a rat interacts with another rat, kind of pre-programming a behavior on an actual rat is quite hard. You can train it with some food, but at the end of the day, it is a master of its own will and it will do whatever it wants. But imagine if you had like a rat looking like somewhat bio-inspired robot that had whiskers and stuff. So in a rat's mind, it is kind of a rat, but it's a robo-rat. So you could then program interactions, and you could actually behave in a controlled environment. So you could analyze, okay, how is a colony of rat interacting with each other, come up with navigation methods and so on and so forth like that. So this is why I started looking into the touch sensing with whiskers, and how you could then mount it on a mobile robot. So as I said, there is like a one-to-one mapping between a single whisker and a single cell in the brain through the neural pathway, and then each of them are individually controlled around the snout, so you can manipulate how they're moving around and understand how the object is that you're touching. Typically, when we do this by the engineering approach, what we do is we have a neodymium magnet, as I explained before. So it's a permanent magnet on top of a Hall effect sensor. And when the whisker touches something and bends, the Hall effect sensor picks up the deflection in the magnetic field, which is how you're trying to interpret, okay, where along the whisker shaft was the contact made, and how does the contact look like? Was it as the tip? Was it somewhere along the length of the shaft, and so on and so forth? And then you use that as a cantilever beam model of bending to figure out, okay, how far from your point of reference is the point of contact? So suddenly you start having this point cloud kind of approach where you're able to detect, okay, touch-based point clouds with the radial distances. So as I mentioned before, so if we were to build a biomimetic or some sort of bio-inspired artificial whisker or a whisker array with multiple whiskers mounted on a single sensor, this could aid mobile robot navigation for ground robots, for marine robots. Think of scenarios where a robot is descending down a very narrow tunnel where there's very limited light. It doesn't have a space to spin around, so lidars and cameras are of no good. But if you have whiskers, it's still touching the walls of the shaft, so it is still able to figure out, okay, where along the shaft it is, still able to localize, still able to understand what the shaft looks like. Also, similar cases where you have, for example, smoke in a room where the room was on fire, vision sensors would typically suffer quite a bit. Where there is smog, the lidars would suffer quite a bit. So this sensor is a bit more immune to those kind of things. Typical transduction methods that people use. So I explained one, magnetic, which is the Hall effect sensing approach, but there could be capacitive, resistive, piezoelectric, optical, and a whole bunch more of transduction methods, each with their own respective pros and cons. And eventual, like the size of the sensor would depend on what kind of transduction you have come up with. So now let's discuss this important challenge. So despite all this, why haven't we seen this as a major go-to sensor in robotics? Or why does everybody, like immediately when you start talking about navigation with a robot, your first go-to is like a camera, either RGB or RGBD or a LiDAR, but why not a sensor like this? So the problem is as follows. So there could be wear and tear very easily because these are typically the whiskers are artificially 3D printed and they may break, they may be having a brittle design. They may or may not be cross-platform compatible because depending on, what was your design consideration when you built the prototype of the sensor, it is not a simple plug-and-play sensor just yet. Maybe it's very confined to a gripper. Maybe it's very confined to a ground-level platform because of the weight and whatnot considerations. Then scalability. As I mentioned, the rat is able to manually, individually control each of the whiskers. So we want similar control in the artificial whisker array as well. So we have attempted to mount servo motors on the whiskers and make them move and control them through motor controller boards. And that means to leave enough range for the servo motors, the max amount of whiskers you can have is 20. So imagine like at every time instance when a contact is made simultaneously, you're going to get 20 points in a point cloud at an instance, which is too sparse. You might want to increase it, but then you have hardware limitations. Then again, it's a black box design. So there are groups in Australia and UK that I know of and I've collaborated with in the past that have built prototypes of this sensor, but they haven't matured enough that it's like a product that I could ask them to ship to me. I plug it into my robot and I start using. So it's a very niche field right now. People are building designs and prototypes in a lab environment, so that there is still scope for further enhancement. Then, as I mentioned, internal noise. So the robot is moving on the cobbled streets and stuff, then it's making noise by itself. So you don't know whether the sensor that what is reporting is a noise or is it an actual contact. So that needs proper filtrations and stuff. And then because the sensor itself is in a very nascent stage, we don't have a very mature perception pipeline like you would get for computer vision, for example. You could go to a GitHub repository, borrow their code, plug it into RAW, start using. So a computer vision kind of problem is more or less solved unless you have a very specific environment that needs some challenges to be tackled. For this kind of sensor, the perception pipeline is like an open book. So there's a lot of work that needs to be done because we don't even have the starting point yet where we say, okay, this is a sensor that has been productized. Okay, now build the product solutions around it. So software solutions. Sorry. So then, despite all these challenges, why are we still looking into this, especially in the groups that I work with and my group as well? So why are we still interested in this? As I mentioned before, so it's immune to environmental conditions, irrespective of whether there is fog, smoke, rain, lighting condition changes, whatever. These sensors are very robust. They have versatile applications. You can detect pre and post contact sensing, texture classification, terrain classification, proximity detection, one sensor, many solutions. So there is still a lot of scope to look into this. Just like cameras are now transitioning towards event-driven cameras, these sensors are already very energy efficient because it's just the energy required to move the servo motor and then the electronic circuit to pick up the sensor feedback. But that's about it. Even if you want to go a step further, you can make it event-driven as well. So then not all the electronics are powered on at all the times. It's cost effective. Although I mentioned that it's brittle, it can break, but 3D printing another whisker in-house doesn't take several thousands of dollars. We are talking tens of dollars, and the material is typically cheap. You buy it in bulk, so you can easily print like 1,000 whiskers. You keep breaking them, keep replacing them. So that's why it's also low maintenance. You break and replace. So where does that bring us to? So this is the first whisker prototype that I built with a group of students over one summer. It was a very interesting project because we added 2 servo motors, kind of like a neck joint, so pivot joint. And then we tried mounting 20 whiskers, as I mentioned, so we knew it was possible, but we didn't get that far. So as you can see, there's a whole jungle of wires here. And some of the components, the voltage distribution was not done properly, so they kept burning and smoking down. And once we started adding more and more whiskers, the wiring got so complicated that it was really hard to debug anything. So we stopped at around 5 or 7 whiskers just as a proof of concept. And this was 3D printed in-house. We built one module first, and then we kept scaling up to as many modules as you need. So we are now looking to, I'm now looking to kind of team up with a group of undergrad and master's students to kind of build a second prototype, second version of this design, knowing that what I know now and how things failed in the past, how we can do better than this. So that's the agenda on my research roster for now. So with that, I'll stop presenting and I'll take on any questions now.
All right. That was fantastic. That's a really interesting research area. Did you?
Thanks.
Yeah. Did you do your PhD thesis in the same topic or
not really, because this is too niche of a topic to do an entire thesis just yet. But I co-supervised students that were doing this in another group that were doing a thesis on this topic. But it was so less on the design side, but more on the perceptual pipeline. As I said, like the whole pipeline is a blank slate. So you have a lot of work to do. So that turned out to be a. But this again is like an offshoot that is a very kind of natural offshoot from that idea.
Great. Yeah. Well, so you spoke about, the problems with adoption and the ability to kind of 3D print these. Are there any open source designs out there that someone could download and build at home?
That's the thing. That's where I am headed. So that's why I'm looking up to team up with students to kind of polish this first prototype. And we are planning to build it open source, open hardware. Normally people go for a patent. So I know some of the groups that have patents. So they built 6 prototypes, of which 5 are patented. And the last one is just like, okay, for research use. The problem is the end product is so big for our use case. As I mentioned before, like their design was meant for a manipulator. So it's not a simple plug and play solution. Even if it had like 10, 20 whiskers, I can't simply plug it into my ground robot and pretend like, okay, now I have a whisker ready to use. So unlike a camera, which is like one sensor fit all robot platform, this hasn't reached that maturity yet.
But that's where you're headed. That's where you're trying to get to.
Exactly. So we take inspiration from how they are arranged in pinnipeds and rats and stuff. But now we're planning to use machine learning and data-driven design construction. So you build a CAD model, but then you optimize it. So you have way more use cases than just a one particular robot.
Yeah, great. Okay, Chris, do you have any questions?
Yeah, mostly really cool idea. I love.
Oh, and
fire
also
stuff, so.
to add to what Luis was presenting before. So I was actually on the call. Maybe I was on another Zoom link or whatever. But I listened to Luis present, and his live demo was very interesting. But the challenge that he mentioned of using Arduino for controlling multiple servos, we faced the same challenge. So we initially started out with Arduino, and then we started plugging our motors in, and then at some point we just gave up. It was like, this is ridiculous.
I think
people don't always realize that. Sorry. I think people don't always realize the extent to which hardware drives, even, you're working on perception and these like theoretical things, but you have to think about the electronics, the processing, all of that, the packaging.
So to add to that, so what I'm telling my students is to have this approach of hardware in the loop. So you can't completely ignore whatever the hardware is doing. But that also means that the hardware needs to be mature enough that if I were to ship the product to you, it's like a Lego kit. You use the diagram, you assemble everything in 10 minutes. Your job is to focus on perception, not to reverse engineer. How the hell do I make the sensor again?
Yeah.
Which is why it is a bit challenging and interesting at the same time.
Absolutely. Yeah. No, I think it's a really fascinating thing, even for like a senior thesis for someone who's graduating from undergrad. I think that'd be a perfect application of that.
So just a plug here. So if anybody is an undergrad or master's students, preferably based out of the US, given the geography constraints, or is able to do this remotely, if you have the resources available to you, like Fab Lab and stuff, feel free to reach out, and we'll see how we can plan out the logistics, because we're currently hiring, well, not really hiring, but like teaming up with multiple students and trying to see if we could build a team and take this forward. So if anybody's interested, I'm all ears.
Yep. If anybody sees this, please reach out. Where do you see kind of the first applications of this going? Like once you have the kind of more general, you can slap it on any application kind of part, what do you think the first step is going to be? What's the first industry that's going to adopt?
So I was basically planning for two industries. So one is, let's say, inspection, especially underwater inspection, where you suddenly have murky waters and the camera is no good. And a single mistake from a robot could cost you millions of a punctured pipeline, right? But this sensor is very compliant, so you are able to detect whatever is happening in the pipeline, but you just have to deal with different kind of physics with flowing water and how it interacts with agile and bendable 3D printed whiskers and stuff. But that's a physics problem. Not saying that this is not solvable, but it complicates the perception side of things. And the other side I was looking at was search and rescue. So as I mentioned, there are scenarios where there could be caustic chemicals suspended that get stuck on the lens camera. Then you can't send a first responder to wipe off the lens and be able to see anything again. So you're only dealing with like a half-dead sensor in that case. But my sensor is like robust in the sense that it doesn't really care whether there are smoke particles, suspended chemicals, whatever else is in the air. It would be able to still detect the environment around you, give you a map of the surroundings so your robot can still navigate and get you to wherever you're going. So even if you're not able to see the person directly, see the victim directly, you still have a structural map of the building, so the first responders can see, okay, where can we crawl through and where can we get to? So there's still hope for the sensor.
Yeah, no, I like that answer. And I mean, to your point with the interactions with fluids, someone in our chat mentioned, this could be used to measure like airspeed or something like that.
Pretty much. So one of my colleagues in Australia has already done this. So, normally when the drones are landing, there's a lot of turbulence the closer they get to the ground. And imagine like if landing on a carrier, like an Air Force carrier. So it's already moving up and down and you're trying to land on it. So these kind of sensors can help you identify a less turbulent area and a less turbulent moment to land. So you could time your landing, something like that. And it's so lightweight that, and if you reduce the form factor, you can mount it on a commercial or conventional drone. Just buy an AR drone and just stick a whisker on it and you'll be good to go.
Interesting. Yeah, no, that sounds like a really fascinating application for this.
Yep.
Okay. Well, that's all the questions from our chat. And if no one on the call has any more questions, thank you so much for your presentation. That was really fascinating.
Thanks so much for having me and giving me a chance
absolutely.
to this idea.
Yeah, we love to hear from, as we said, we'd love to hear from all ranges, all ability levels within robotics. So it's really nice to hear not just from hobbyists, professionals, but also from academics like yourself. So thank you again for your time. We really appreciate having you on. And with that, we'll move on to Ishant. Have a great day.
Hey everyone, how are you?
Good, how are you?
Doing great.
Great, well, feel free to share your screen or whatever you need to do, and we look forward to seeing your presentation.
Awesome. Well, let me just share my screen real quick.
Mhm.
All right. Can you see the screen now?
We can see it.
Awesome. So, hello everyone. My name is Ishant, and basically I'm the founder of this startup called Zero. So at Zero, what I'm trying to build is basically revolutionize the way we interact with technology. With one of my personal goals to bring bring personal and social robots to every single household in the entire world. So let me just go through the main problem that I was trying to solve. So the biggest problem that I was trying to solve, not from the hardware perspective, but from the software perspective, was while building. While building my own conversational AI, something similar to how Alexa and Google Assistant works. What I realized was there was a huge, big system architecture problem with the conversational AI that we have right now. And just to the problems with the system architecture of these current state of the art conversational AI and digital assistants are, first of all, as a poor user experience that it delivers, and on top of it, as a third party developer, if you wish to build upon these AI models. So, for example, Alexa provides SDKs to build skills for Alexa. But it's very hard. You won't find any useful skills for these devices, and the reason behind it is, as a developer, you are very constrained when it comes to what kind of applications you can actually develop using these underlying technologies, because the conversational and natural language processing models and AI models in general are not inherently very modular and very scalable. So what I mean by that is, if as a company, if you wish to add even if we look at Amazon itself, and let's say Amazon decided to add a new feature to their digital assistant, they would have to collect a whole data set and then retrain their entire AI model just to add that new functionality, which is obviously not very scalable and cost effective. And like I've already mentioned, the poor user experience. Most of us have a smart speaker at home, but there is no personal connection with your smart speaker like you have with your, let's say, your smartphone or your personal computer, right? So these were some of the problems that I was trying to solve. So the solution that I came up with was to basically, I decided to build my entire conversational AI, the whole system architecture from the ground up, that is scalable as well as modular. So, and one unique thing that I was really aiming to do to achieve is to allow developers to build desktop and smartphone level applications, but with voice user interface. So, and this is something which is really cool because, like, if you look at the evolution of consumer software. So we went from software with just terminal and a keyboard as a user interface to introduction of a mouse, to then having smartphones with touch screens. And now if we look at the general path of the evolution, the next evolution of the user interface for software is going to be conversational AI based. So, but right now there is no standard framework to enable it. So what I'm with at Zero, what I'm also trying to achieve is to create a standard framework for developers to build this next generation of consumer applications with a hybrid of graphical as well as a conversational user interface as its primary UI. So thinking about the problem, so when it comes to deciding like what should be the solutions for it. So to solve the system architecture problem that I previously mentioned, I finally decided to build an entire operating system. So it's the operating system that I'm building is called Osmos. It's based on Linux kernel, but I'm building everything on top of it from the ground up. So integrating conversational AI models, everything. And a cool part of the operating system is sorry, that the most of the AI modules and AI models are actually running offline on the device, so they are very integral part of the operating system. Because one of the things that I'm really passionate about is the user privacy and security. So instead of streaming your voice and your commands to a third party server, all the AI inferencing should be happening offline on the device. Second thing, to solve the personalize the problem with smart speakers, that is like poor user experience. The AI that I'm building, it should be adaptive. That is, it monitors and it learns from the users routines, likings, dislikings, and molds its personality, molds its responses according to that. And one more thing that I realized is just having a cool AI and a cool software is not enough. There is a very hard need to have a interactive hardware as well. So that's where the whole concept of having a social robot comes. So personally, from a childhood, I've been a huge fan of social robots, and it's been a personal passion of mine. So what I decided to do is integrate this awesome artificial intelligent operating system with a cute and interactive personal robot. So that's where the second product comes, that is Asper. So Asper is a personal robot that personal companion robot that I'm building. We can look at the market validation. So, like in American household right now, every 1 in 5 household right now has a smart speaker. But looking at the customers' feedback, more than 70% of the users are concerned about their privacy. And even if you look at the recent growth in our smart speaker market, that is, since it's growing at a 17% rate, the biggest contributor to this growth is actually smart displays. So it's again a great validation that people are willing to pay more for a better user experience than just having a simple speaker, right? And then we also have chat GPTs as well. So let me just go through a bit more detail about Osmos. So Osmos is one of the world's first operating system, artificially intelligent operating system that is secure, private, it works offline, and it is adaptive. And the goal, like I've already mentioned, the goal is to enable the next generation of applications that have conversational AI and graphical user interface as their primary user UI. And so, and again, so if you look at some of the application examples that I have given, so this is an example of the email suite app that is running on Osmos right now. And then there's a health tracking and basically yoga assisting robot where Asper is actively tracking your body posture using the onboard camera and body positioning, and all the AI model is running offline on the device, and it is basically guiding and guiding you throughout your yoga. And again, and plus on top of it, I'm actually providing the SDKs for developers to build applications on it. And the one thing that really differentiate basically highlights the benefit of having an operating system instead of having a traditional cloud-based AI is, instead of building these skills which are basically just web apps, on Osmos, you as a developer, you literally build native applications just like you would build for your smartphones. And even for the front end user interface, I'm actually adding support for Flutter as well as some and Electron and Tauri. So basically, any web developer, any developer who has experience building applications for smartphones and computers can actually build application for Osmos as well. So the opportunities are quite literally endless. So again, and coming back to Osmos, so I'm coming back to now Asper. Matter of fact, I got Asper right here with me. So Asper is basically designed to be a cute little companion robot. And if you notice, so Asper can like turn around, move around, navigate around. It has a camera right here. It has a head, so 2 servos in his head. It has a touch screen with expressive face. And one thing that you will notice, it's a robot, but unlike traditional robots, Asper don't have any wheels, so it's again a very conscious decision that I came up with. This particular version of Asper is actually, if you look at it, it's designed to sit right next to you at your main desktop workstation, at your kitchen countertop, and it is designed to basically take commands and basically what Asper allows you to do is keep your life. For example, in my case, while I'm working on something, I can keep my 100% focus on my main computer, while I can delegate all my emails, my notifications, and all those stuff to Asper just through voice command. So that's the first implementation of Asper. And looking at the cool part of having a cute robot is, instead of it targets a huge demographic of audience. So if you look at Asper, since it's a cute robot, it's a great companion and educational robot for kids. So kids can a much better alternative to iPads. I would say it's a it's a productivity tool for working individuals like me and most of the audience. And it's again a really great, easy to use assistant for elderly generation. It's a great health companion for them that keeps track of their medications. It keeps track of their heart rate of your elderly generation, elderly parents, and keep you updated about their health as well. So yeah, so if I like go back, and I would like to share some more details about Asper. So let me just show everyone some of the prototypes of Asper and how it all started. If the internet allows me to. Wait, that's the wrong video. Yep. So this was actually the first version of Asper. It was just a Arduino based hacky robot that I built for myself. And this particular version of Asper was actually quite special because it was basically a health companion robot inspired by the Baymax from the movie Big Hero 6. So it was a health companion robot. So if you see, there was a little display, 7-segment display on the chest of Asper. This particular prototype, and I had I had a smartphone app where I could prescribe my health symptoms. Let's say I'm having stomach ache or headache, and I could just enter my symptoms, and the robot Asper would prescribe me medication. So it would display the right medication on the screen, and it would notify my parents about my health condition. So this was actually a quite useful earlier prototype of Asper. Here you can see the Asper got a bit more advanced. Now it had a proper screen. It had a camera for face tracking, and of course, if you notice, the earlier prototype of Asper had tracks, so it could move around. So again, going to the next prototype, it was more polished. Fun fact about this particular robot, it caught fire I don't know what happened, but it caught fire, and yeah, rest in peace, little buddy. And now this is the latest version of Asper. So as you can see, it's a more of an interactive version of Asper. Matter of fact, I would share the links to the YouTube videos as well, so everyone can see the videos on their own. There's also a demo. If you guys go on my YouTube channel, there's also a demo of the old version of operating system of Asper. Where I have demonstrated all the applications that Osmos was running back then. I'm working on the latest version of Osmos. I'm quite excited to share it. Again, if you look at this as well, I would again suggest everyone you can go to r/Asper to keep yourself updated about the regular updates that Asper is having. But what I'm showing right here in this particular video is actually the Blender plugin. So Asper, since Asper is a social robot, it being interactive and animated and expressive is essential for it. For me to, so here I have actually built a plugin where you as an animator can easily keyframe your animations in Blender and actually live stream it directly to Asper. And here in this particular video, what I'm showing is a particular deep neural network model that I've built called Audio to Vysims. So for all of you who are not familiar with Vysims are basically just a subset of lip and facial expressions that we make while making certain voices. So what this particular model does is whenever Asper is saying something, this model is running in real time, and in real time it transcribes the audio that it's outputting from its speaker to the appropriate facial expressions and facial vysims to look really natural and expressive. So all these facial expressions, none of them are pre-programmed, and they are actually animating it in real time, and along with the body animations as well. And then there are other features as well. So for example, direction of arrival, where the user can stand in any direction, any place in the room, and can call Asper, and it would basically face you directly. And again, this particular video here, I'm showing a demonstration of the operating system itself. It's more of a UI demonstration of the operating system. So yeah, so this is the coming back to the artificial intelligence part. I'm really excited to basically launch the operating system as well. So if everything goes well, the operating system will be live for everyone to use and download by this month, or maybe most definitely by next month. And I'm also planning to basically launch Asper as well. So this particular version is partially ready for production, but I have some few kinks to iron out, and very soon Asper will also be available for everyone to buy as well. So yeah, I think I have taken enough time, and I'm ready for any questions that you guys might have.
Yeah, great
Thank you
presentation.
so much.
I really love the design.
Thank
Somebody
you.
in the YouTube said it looks friendly, and I agree.
Yeah, that's the goal.
Yeah, I was going to say, as we said earlier, the skills to make a robot and the skills to make it look friendly are often very different, right? So it's really impressive to see someone who can not only, use their technical acumen to build a robot, but also use their design acumen to create something that is friendly and welcoming. Someone in the group chat or in the YouTube chat says, are you aiming for open source or closed source for this?
So the goal is to keep most of the parts open source. So there will be some AI models that I'm working on that will still be closed source for now, at least for a while. But most of the operating system part will be open source, and I'm planning to start making some few of the repos public maybe this month.
Okay.
On a sort of related note, YouTube also asked if I guess there are some big players in this kind of companion robot, helper robot. Even Alexa is potentially a competitor, the Echo. How do you feel like you fit in that realm?
Sure.
And being open source is potentially a plus there.
Yeah, so being open source is a potential plus. Again, it's all about the approach with the AI that I'm taking. So the reason that I've decided to build my whole conversational AI from the ground up is the benefits that I have is, first of all, the entire AI, the NLP and NLU models are actually working offline on the device. So one of my main strengths was that I am able to optimize my AI models to a certain level where I can run these models on an edge device. Plus, on top of it, the main big thing that I'm doing is basically creating a framework, this particular framework that I mentioned, where developers can build native applications with an integration with a graphical and conversational user interface, hybrid of graphical and user interface. So I'm hoping to basically have this as a good enough an advantage for a while.
Hi there. I didn't catch the whole of the presentation. I apologize for that. I really like the idea you've got, and I one thing that I thought of is potentially if you've got very good solutions for the social robot part of a robot, you could be potentially selling this to extend the existing functionality of a wheeled mobile base robot or a robot arm. Or so if people are developing another robot and then they want to add the functionality for a social robot, this can be used to kind of extend that quite easily. And if you're developing tools that are very specific to social robots, which is a very different kind of robotics because it's so much more based around people and robots.
Yep.
So I like the focus there and the way that you can kind of contain that focus using your head and software.
Yeah, so that's the goal. The goal is to basically, so Asper and Osmos are two different products. So Asper on its own is running operating system, and it's leveraging that operating system to be a great social robot. But as Osmos on its own, since it's an artificially intelligent operating system, and the goal is to make it as general purpose as possible. And since I know, but the thing is, I'm not trying to replace, like, say, a Windows or Mac OS. I'm trying this operating system can be used to power industrial robots, medicals, and surgical robots. Just imagine a surgeon during surgery can just ask the robot to perform a particular task, or ask the robot to fetch the patient's history just directly to the robot. So that's where it's a great implementation of the operating system. And automobiles on its own is also a great implementation, where as the operating system, this conversational AI based operating system can be installed in cars and essentially convert the whole vehicle into a companion.
I would suggest that you kind of would keep the focus on the social.
Right now, since I'm starting, my focus is on building a personal social robot.
It could be definitely. I could see it being used in an automotive application or in some medical settings. But when you're actually doing a medical robot, then there's all kinds of different rules, and automotive is again all kinds of different rules, and you wouldn't want to be doing those two things at once.
Yeah.
I like the idea of if you were building a robot dog or a robot human, you would have a separate computer in the head that was running this software, and that was then just taking care of it all whilst the rest of the body does its own thing.
Yep.
And sorry, thank you.
Cool. Well, I think that might just take us to the end of the third Reddit Robotics Showcase.
Awesome.
We did it.
Thank you so much, Ishant.
Thank you. It was fun talking to you guys.
It was great having you on.
Awesome.
If you want to go ahead and stop sharing your screen, we'll do our quick wrap up. And
right, okay, then in which case, I thought I was waiting for an outro then. Okay, thank you everyone. Yep, for those of the few of you sticking around, but for those of you who are watching on catch up later on, this has been the third and possibly final Reddit Robotics Showcase, given the climate at the moment for it. But it has been wonderful to see the robots coming from the community and as well from academia and industry. It's a very unique event for all ages and abilities, and it's really nice to see all the kind of cool things that people are actually doing with robots, not just claiming to be able to do in their papers. So thank you very much, and wish you all the best in your future robotics endeavors.
Yeah. One last big shout out to all of our keynotes for heading up this stuff. We really love seeing all the cool stuff you're doing, and we know it takes a lot of work to do the longer 40-minute presentations. So once again, thank you to all of our keynotes for being here for us and presenting.
Definitely check out Viam, check out Scythe for jobs, both of them. Check
AMP
out
as well. Yeah,
AMP as well. Yeah, wonderful. Right, thank you very much.
If we're doing shout outs, of course, one goes to Ollie for being our fearless leader, for driving this forward another year. this wouldn't happen without you, and I know that's been a bit of stress for you, but
I
we all
appreciate
appreciate
that.
it.
Yeah, it's well, yeah, thank you very much. All right,
Absolutely.
and likewise to you guys as well for all your support. Okay, let's call it. Right. Bye, everyone.
Until next time.